Uh, that's me, Dr. Bly. The GH is silent. It's spelled like Mutiny on the Bounty, Captain Bly. In fact, I got a captain in my family. My brother's an airline pilot, or retired. I think they're forcing them to retire at 65 now. Used to be 60, but they were kind of running short on pilots, so they let them go another 5 years. As long as they could see straight, still have all their mental capacity.
What airline did you work for?
I'm sorry?
What airline did you work for?
American Eagle. Yeah. He was based in Miami. And if he needed to pick up a flight someplace else in the country, he'd just hop one of their planes and fly there in a jumper seat. Well, let's see, where to begin? Is everybody familiar with how to get into the course in Brightspace? You don't have any trouble getting in? Okay, that's good. Have you had a chance to wander around in the course and see what's there? No? Okay. We'll take a quick look at it. I need to share. Before I get started, every class meeting we have, I Zoom it so that I can record it. That's the primary purpose. I want everybody here, especially if we have a lab, which is most of the days. But I Zoom and record, and then I take the recording and process it for mistakes that I make, which are occasional, and put the things together that I want to be together. Maybe make an additional comment overlay on the video. And once I get it processed and in MP4 format, I upload it to my YouTube channel. And then in Brightspace, I put the link to that. So when you click on the link in Brightspace, and I'll show you where that is, it's going to take you to YouTube, and you probably have to endure commercials every now and then. But I'm not monetized, right? So you're not donating any money to my account by accessing these videos. Okay, so let's look at Brightspace first. Let's see, I need to share the screen. That's one thing about this location, is the internet is so slow. I can go out to lunch and come back before we. Okay, let's see. Well, where is it? I need more windows. Where are they? Is this it? That must be it. Share that screen. Come on. There it is. Yep. Okay, so in your browser, of course, you want to go to, let's see, can I get this out of my way? Yeah, you can see that. There we go. And I want to go to, well, this is where I was. So I'm already in the course here. Let me back out to the home page. Right, and then I go into the course. Okay. You don't have to stop here. That's just a welcome message. So you've had other courses with Brightspace, I assume. So you're familiar with it. Okay. So I'll just highlight things that, so if you want to see what assignments, I'll tell you what, better yet, I better do this as a student. Otherwise, you're going to see a bunch of junk that's hidden from the general public. There's assignments, and the assignments, the only thing you're going to see in assignments are the extra credits. One of them, you picked up the periodic table. There's a sign-in sheet over here. And then grab one of each of these in front of everybody. And then find a seat wherever you can. So there's a periodic table. That's the one for this exam, and you probably wonder when it's due. It's due on the day of the exam for exam 1. That exercise, and the instructions are copious. Then this extra credit comes under exam 2, so I won't hand that one out yet. The rest of them are going to be laboratory exercises. And you can access them from here, or you can access them from course contents, either way. If you want to find people in your class, of course, you already know this, don't you? There's your class list. And you can email anybody or everybody in the class that way. And that's how I'll communicate with you guys, with the Southern email system, your email address. Okay, so here we go into content. And everything is under Start Here, Lessons and Resources. There's another copy of the syllabus. In fact, everything that I hand out here is duplicated in here. So if your dog eats your homework, you can go find another copy. Okay. I just do all these copies so you don't have to spend money and burn up your printers. So there's the syllabus. There's my schedule. Actually, the syllabus has my schedule buried in it. So I gave you a separate copy of my schedule. That's the pretty one with the reds and the blues and that stuff on it. It's also in the syllabus. Right, so you got 2 copies of it. And what that tells you is, let me just call it up. What that tells you is where I am at any time during the day. Monday through Thursday, of course, I'm on the Raleigh campus. Yep. Question? No? Okay. I'm on the Raleigh campus of New River, and I only come down here on Fridays. So if you want to see me in person, this is the day. If you want to connect with me by Zoom, these are my office hours here. These time slots there are office hours, and then I've got a time slot there and there. So I've got 10 office hours, but that's just to satisfy management. New River says I have to have 10 office hours scheduled. But if you need to contact me, just send me an email or text, which should be on the my cell phone should be on that first page, I think, in the let's see, yeah, there it is. And text me a message if you need to meet, and then propose a time that's compatible with this schedule, and I'll send you an invite. So then all you have to do is click on the link and we can connect. So I only list face-to-face classes here in their time slots. My virtual campus, the web-based courses are all down here in the yellow, so they don't matter really, not as far as timing goes. Okay, that's my schedule. Actually, if you know how to connect on your phone with using Zoom, if you have the Zoom app on your phone, all you need is either to click this link right here or to use that ID. I don't have, for my personal meeting ID, I don't have a, what do they call it? Passcode. I don't have a passcode for that one. So all you need is that ID to get in. Okay, stop me anytime if you have questions. And I'm going to go back. Let's see. Oh, there were breadcrumbs. I could have followed the breadcrumbs. There's a copy of the syllabus. There's another, my office hours link. You can click that one too. Multiple ways. This is where we attend the Zoom meetings. Right? Just click on that Zoom link. Can you see that? Yeah, see that. And it should have all our meetings here. And of course, the current one is this one, which has already started. And it says start here. Does that mean I'm already connected? Must be. Because that's today. And where does it say I'm recording? Should say somewhere I'm recording. Maybe it won't say as long as I'm sharing. I hope I'm recording. Well, my camera's on. I have gone through whole lectures and not recorded. So when it was important, I just after the class was over and I discovered the problem, I'd just go back in there and do the whole class over again. I don't like to do that, but I have done it. Okay. So let's go back out. Let's see, that one we don't need. This gets kind of busy in here, doesn't it? There we go. All right, so there are your breadcrumbs, right? You know about those. All right, what else? What else is important rather than wasting a bunch of time? Here are the modules, exam 1, 2, 3, and 4. That's all. We have 4 exams. I'll point out one of those handouts is a periodic table, right? And it's got red boxes around some of the element symbols. Right? If you don't already know those symbols, then memorize them. What does that symbol represent? It represents an element. So the symbol corresponds to an element. That's about half of them in the periodic table. Right? There are 118 elements in the table, and there are about 60 there that I want you to memorize. Right? Have you got to chemistry yet in MLT? No. Are you just starting this semester? Okay. That dumb question then. Okay. So unless you memorized them in high school or in another course, then you need to memorize those symbols, the ones that are surrounded in red. Anybody got an idea how to memorize stuff like that? Index cards, right? Put the symbol on one side and name on the other and just drill them, right? Right hand stack, say, is the one you get right. Left hand stack is the one you get wrong. You go back to the left hand. Keep doing it until they're all in the right hand stack. And you go back and do it over again. Symbols, naming them, and then go through names and symbols. One thing you'll notice about the symbols is some of them have single letters. They're capitals. There's a sign-in sheet up here. And you'll need a copy of everything here. We'll talk about this in the class. It's right over there on the end of that table. If the symbol, if there's only one letter, it's going to be capital, like carbon, like just a big C. But if it needs 2 letters, because C is already spoken for, that's carbon, then you need 2 letters, then the second letter is always small. So if we say calcium, it's going to be a small a. Large C, small a is the correct way to write it. If you write large C, capital A, it's wrong. Okay, just a word of warning. I know some people like to write everything in capitals, right? I don't know too many of them, but it could get you in trouble if you're used to writing that way. Okay, so under exam 1, you'll find you'll find the PowerPoints that I'm going to use for lectures. Right, so you can get an extra copy of the PowerPoints. One thing you'll notice is if you have Microsoft Office, you can access the actual PowerPoint slide set. If you don't, if you're somewhere and you can't do that, then there's a PDF copy here. The only thing, it doesn't have any animations in it. But this one does. This one is an HTML5 conversion of the PowerPoints. And all you have to do is click on it. It'll come up in your browser. It'll have everything, animations, embedded videos, all that stuff. Okay, so that's chapter 1, 2, and 3. I have a bunch of archived recordings. I just put them in this folder so they won't get in the way. If you want to go back and look at some older stuff, right? Look at the really old ones and have a good laugh. Because the quality is pretty bad. We're getting better and better as time goes. The best thing we did was move the lecture part of the course out of another room into this room. I used to have to do the lectures in a different room because this room had no audio visual in it. And I have to have my PowerPoints. So those recordings are pretty bad. But now with this new stuff, the last couple of semesters, it's nice. There's a sign-in sheet right over here. And then you'll need to grab one of these. Well, if you're going to be late, this is the best time to do it the first day. You didn't have to drive through a flood, did you? Oh, hour. Oof. Anybody else have to drive an hour?
I do.
Oh, whew. Are you closer to Beckley than you are here? No. Okay. I drive an hour and 3/4 to get here. So if you're an hour in direction toward Beckley, you might be better off taking a course like this at New River. Be closer. Too late for that, right? You're stuck in this one. Okay, so those are old videos. Take it or leave it. Then the review. We're going to have, you can pull out your syllabus, and there's a schedule of classes on page 6. That tells you every day during the semester and what we're going to be doing on that day. I've highlighted the ones on the left, the exam days. And notice on exam days, let's see. Let me check before I say, I don't want to misspeak. Yeah, on exam days, we don't have labs because we have the exam and then we go into the next chapter. So that gives you enough time to do the exam and then enough time for me to talk and introduce the next materials. So we don't have to squeeze things and get another lab in. So the labs don't occur on exam days. So the review, this last document on this side, on this end, is my review document. And that piece of paper above it was the answers to the review. And notice it's structured like an exam. It's all those multiple choice questions. Some of my students like to take those things and drill them as exams. They'll just go through and answer it and then check their answers with the key and go back and they know which ones they're weak on and they concentrate on those. That's one of the purposes of it. And then the other purpose is I take that review document. There's a lot of repetition. So I take out unique examples of questions in there. And then on that day that says review, we go through them. But before I do that, bring any problems you have with those questions, because we do those first before I start talking. Okay. That's review session. Yeah.
Are the exams going to be on a piece of paper or computer?
No, it'd be on paper.
Oh.
Yeah. Yeah, you need to be in person. The advantage to that is not just that I see everybody here and I can proctor the class, but I'm going to grade those exams before you leave the room. So you don't have to wait for them. Because if you have to wait for them, then chemistry is a cumulative science. In other words, the stuff you learn now, you're going to need to know subsequently. So the sooner you know where your weaknesses are, the sooner you can work them out and be able to progress through the later chapters. So the sooner you get your exam results back, better. That's why I want to grade them before you leave the room. Unless you have to split, sometimes family issues or work or whatever. Nobody in here has jobs on the side, do you? You do have? So you're in MLT and you're working too? Okay. All right, that's a tall order. I mean, I went to school, I worked my way through school too, so I understand where you're coming from, but it's not easy. And then you have bosses that want you there at a certain time, and that's when your class meets, right? Okay. If that ever happens, then that's where the recordings come in. You can watch the recordings. You'll be absent, but you can get the recordings. Now, if you're absent during a lab, you got to depend on your lab partners to supply the information you need to complete the lab, right? Because they can't do it for you. All right. We'll talk about the labs more later. All right. So let's see. This homework optional, that's only if you're really, really aggressive. This document has a list of problems in the back of the chapter of your textbook. So those numbers for each of those chapters, 1, 2, and 3. Let's see, is this showing up there? Yeah, 1, 2, and 3. Those I've selected as optional homework. You don't have to do those. If you're pressed for time and energy, focus on this review document. Okay, that's where you'll get the most benefit. But in chemistry, like most sciences and math, the more problems you work, the better. Because problem solving is where it's at. This lecture that I'm going to do just introduces the topic. Review and working those problems, that's where you learn the science. And I might as well say it now. Your two best friends in chemistry, number one is curiosity. You feel like you never know enough. You want to know more. That's a good sign. And the other is boredom. You work on these problems and you work them, and there are lots of repetition. You work them over and over and over again, and you get bored working them, then you probably know that type of problem solving technique, and you can move on to something else. But if you've got curiosity and you're bored, then that's a good sign. Okay, let me see. I want to back up. See, I've already used up almost 25 minutes. That's a bad habit. I just can't stop talking. There's my contact information again as a separate file. Laboratory exercises are in a separate module. So here, I've set it up so that ideally, when we do a lab exercise in here and you complete it, then it's due the next time we have another lab exercise. So in this case, the first one, the safety lab, is due next week. And we're going to do introducing graphing techniques next week. And that one will be due the week, 2 weeks after, because we have an exam in the middle, right? On the third week, we have an exam. No, wait a minute. One, today, next week, following week, fourth week. Now, this is the first week. Fourth week, we have an exam. And that day, we don't have a lab. So the lab before that, the lab techniques, is not due on that day. It's due on the next time we meet for a lab. Does that make sense? Okay. So that's the way it should be set up. I have made mistakes before, but I think it's right in here. If you find a mistake, contact me, right? Or if you think it's a mistake, that's fine. You won't hurt my feelings by telling me. I'll just check into it and see if it is a mistake. If it's not, then I'll try to explain what it actually means. And that goes for exams too. If you think I've misgraded an answer, bring it to me. We'll see if I made a mistake or if we need to discuss the correct answer. Okay, so those are all the labs. Let's see, I think there are 10 of them. Yeah, we have 10 labs. Okay, I'll point out one other thing. There's one day during the semester that I'm not going to be here. So you don't have to be here either. Unfortunately, the president of my college at New River has scheduled our semester, what do you call it? We call it Institute, Faculty Staff Institute, where everybody comes together in one place for a meeting. Right? They do that here too. But she has scheduled it on October 6th, that Friday. So I have to be there. So how are we going to work our way around that? Well, the only thing I've got scheduled on that day is review. And for that, you need to view the Brightspace video for the review. And I'll have that one up. It'll be in there just like the rest of them. Only it'll be the wrong date. It'll be last semester. Okay, so just you'll have to watch the video and If that's not good enough, if that doesn't satisfy, if that doesn't answer your questions, then contact me and we can meet a Zoom meeting and figure it out. And since you're all in the same boat, most of you anyway, is everybody in here MLT?
Yeah.
No strays? Okay. If you all put your heads together and decide that this particular problem is a mystery to everyone or to several of you, then we can schedule a group Zoom, and kill 4 or 5 birds at once. Okay. That's the only bugaboo in there. Good news is there's no final exam. There's no time for a final. Right? We just have the 4 exams plus the labs, and that's your grade. And the grading scale is on page 2. 70% for the exams. Right? That's the value of your final grade. And laboratories, 10 laboratories represent 30%. So each one is worth 3% of your grade. What's 4 into 70? 35, 17 and a half. So each exam is worth 17.5%. If I did my math right. I try to do things in my head sometimes just to keep things spinning. At my age, they tend to slow down really quick. Because of rusty gears and such. Okay. All right. So does anybody have any questions about the structure of bright space and where to find things? Okay. Let me pull up the let's see, stop this share. And let me share the syllabus and see if there's anything else odd in the syllabus that we haven't talked about yet. Come on. There you go. There it is. Let me get this out of the way. Come on. Here we go. All right. So this is not the first course you've had this semester, right? Because this is Friday. You probably had a couple already, right? So you know that they changed the structure of the syllabus this year. I don't know if it's good or bad, but this is it. Let's see. We talked about the textbook. Everybody got a textbook? Okay, that looks familiar. Okay. All right. The lab manual, right? You probably had to buy the lab manual. If it's sealed in cellophane, it's not. You didn't get a lab manual? That's okay. You don't need one. It wasn't listed? Okay, they left it off. Well, that's fine. As long as we don't get caught violating copyrights. Some of the labs I copied and I've edited them, significantly edited them. Some of them are not even in your lab manual. But the reason I generally have the lab manual in there for you to buy is so that if anybody questions copyright infringement, then you've got a copy of it. So when I hand out the hard copies that I've modified, you can say, yeah, but we paid for them already. So there's probably fine print in there that says you can't modify them either, but I do it anyway because the lab manual's just not quite there. Okay, so no worries. You don't tell, I won't tell. You're going to need a calculator. Everybody got a calculator? Now, any other time during the course, you can use a calculator on your phone. But for exams, you have to have a bona fide scientific calculator. Because smartphones are just way too smart. I don't want any smartphones in my class during exams. So you need a calculator. They're really dirt cheap. I've got the functions that you are going to need are listed here, but if you find a calculator that says scientific on it, it'll have everything you need. You don't have to deal with the details. Lab materials. You're going to need a lab coat, right? So everybody, you're in the MLT program, probably have a lab coat already. Right? Did they tell you where to go to find one? Or did they sell you one? Oh, you have the disposables. Okay.
That's the ones they gave us.
Okay. Well, you can bring, instead of throwing it away, you can bring a disposable to class. Okay. That's fine. I bought a brand new one because my old one was, it was pitiful. I've had it for 20 years and it had stains in it I couldn't get out. So this semester I bought a new one, and I found a location near Beckley where you can still buy lab coats. I mean, those places are hard to find. I know there's one in Dunbar, right? If you live that direction and you want a lab coat, there's a place there. But I don't know in this immediate area where you would get one. A lot of my students buy them online. If you want a permanent, so to speak, lab coat, then online might be your best bet. But we also have some disposables in the back if you walk off and forget. We'll talk about safety things later. I just want to get those out of the way. Eye protection, we have goggles and glass and protective glasses, but they're so old, they've been used so much, they've probably got lots of scratches in them. So if you have a pair that you can bring, you'll probably be happier with it. Unless you wear glasses that with unbreakable lenses, that's fine. That'll protect.
Would these be good for the lab?
Yeah, that's fine.
All right.
Yeah, we're going to be doing anything that's so hazardous. You need face masks, right? Big shields. We've got a couple of them back there, right? If you feel more comfortable, but just protect your eyes. And we provide the gloves somewhere. I might have to bring some from Beckley. It's kind of hard to get supplies here. Okay, so there's a grading scale. We skip over that. You don't need to know that. Regular exams, we talked about that. That the format is just like that review document. Makeup exams, that's kind of hard to come by, right? Because we only meet once a week. So when are you going to make one up? If you have a real family emergency or something that keeps you from taking the exam on that day, then we can work something out. But it's just a pain. So try to be here on exam day. Everybody knows exam etiquette, right? Nothing but your pencil, the test. You can have some scratch paper, your calculator, and everything else is on the floor under the desk out of the way. And we're kind of scrunched in here, so we're going to have to be liberal with the spacing. Right? Just don't look at your neighbor's paper. Don't make me think you're looking at your neighbor's paper. That's probably more accurate. Because I have a solution for that. And it's not just to kick you out of the class. Right? If I have a strong sense that somebody's cheating, next time you take an exam, it'll be special. Right? Everybody else will take one exam and you'll take a special exam. Okay. Now, I haven't had this happen before. I've had to do it a couple of times, use that scenario. And the reason I do it is because the process, the administrative process for dealing with cheating is just a nightmare for students and for instructors. So I like to handle that stuff in-house. But if I do give you one of those special exams and you ace it, then maybe I was wrong and you weren't cheating after all, right? So if that's the case, I'll admit it, right? I'll come to you and say, you got a special exam and you aced it. I'm sorry, I accused you of cheating. You know, I'll eat crow. Let's see, lab exercise reports, right? All of these lab exercise reports in this class are completed on the hard copy. Right? Just do the calculations there, fill out the answers, gather your data and observations, then answer the questions on the hard copy. We don't have any formal reports in this version of chemistry. Now, if you took 101, not 101, and this is 213. If you took 213, you'd have to do formal reports. But I cut them some slack. We don't have 10 labs in there. We have like maybe 6. So that gives you a little extra time to put the reports together. But you don't have to think about that. This is probably the only chemistry course you need, right, for MLT. Okay. Besides, medical lab techs, you have a fairly rigid way of doing things, right? It's dictated from on high, right? Some government agency is telling you what you have to do to be certified, right? As a lab or as a technician, and you got to do it a certain way. So I don't see much use in forcing you to do formal lab reports, because you're probably not going to have to do them that way anyway in your line of work. Okay, if you ever want to do research and publish papers, then that would be a handy skill to have, but nobody in here is going to do that, are you? But is anybody going to go from MLT to MLS lab science? Okay, so you're going to get a bachelor's degree to be MLS, right? Hopefully. Okay. They may have you do formal lab reports in that series, right? Okay. Let's see. We've talked about this one already. And let's see if I have any. No, I don't have any addenda. Okay, that's it for the syllabus. All right, what do I want to do next before we get to the lecture? Maybe I'll talk about the labs. No, because we're gonna have to. Let's get the chapter. I'm going to do chapter 1 and 2 today. They're short chapters, so we should be able to get them done. All right, so let me change my header up here. First one is going to be chapter 1. And what's it called? What is it? That's a review document. Yeah, you need one of those, right? And that's the answer key. There you go. And that one is extra credit. Did you pick one up already? Because there's supposed to be enough for everybody. Wait a minute, I got extras. Oh, wait, 2? Okay. Good. Okay. That means I don't have to carry any of that stuff home. Okay. What was I going to do? Figure out what the name is. Basic concepts. For those that came in late, you might wonder what all these geometric shapes are on the board. The early ones. Anybody want to tell them what they are?
Oh, those are blind spots.
Those are glares on the video, right? You may not be able to see them there, but the camera picks it up as glares. If I write in those spaces, then the video will get washed out in those areas. So I mark them off, so I'm sure not to write in those areas. It's just one of those things we have to do we don't like to do. Okay, so let me share. Come on. Let me share. Here we go. Chapter 1, right here. Come on. There it goes. Okay. Now let's make a slideshow out of it. Okay. I think we're up and running. See if it'll go. Yeah, it's progressed. That's good. All right. I always hand out these copies of the slideshow so that you can scribble on them if you want to. If you'd rather take notes in your tablet or on a piece of paper, that's fine. but you have the hard copy there if you want it. Chapter 1, basic concepts. First of all, let me see, is that in here? Yeah, that's an outline. All right, so we'll skip over that. Chemistry. Have you ever had to define chemistry to anybody? Probably not. Chemistry is a very broad subject area. In fact, my 213 class uses a textbook that's called Chemistry, the Central Science. Right? That's not conceded. But chemistry does feed, it either feeds into or it's fed by lots of other areas in the sciences. And sooner or later, if you deal with any type of other science, you're going to have to touch on chemistry sooner or later. Chemistry basically is a study of substances, right? That's broad, right? Substances and the changes that they undergo. Right? So those could be physical changes, those could be chemical changes, and we have to define what those are a little later. But these transformations are covered under the umbrella of chemistry. Anybody take a science course in high school? Right? So you probably had to define what matter was, right? Mm-hmm. So, right, has mass, takes up space. And includes anything and everything in the universe that's not classified as energy. We got matter and energy. And for the longest time, scientists believed that never the twain should meet. They were two separate entities, right? Then Einstein came along and muddied the waters, right? He proved that matter and energy are interchangeable. That's how we get atomic energy. The atom bomb, or peaceful uses of energy, is conversion of matter into energy. But in the chemistry, we're going to stick with the situations where matter and energy are separate. In other words, I'll say this again later. During a chemical reaction, you don't create matter, you don't destroy matter. Right? You put reactants together and you get products. The mass of the reactants equals the mass of the products. Right? And any energy that's produced, while it's probably due to matter transformation, is so small in a chemical reaction that you can't measure it. We can't measure it. So just ignore it. All right. So when people with a curious mind look at nature, they make observations and they very often have questions. Why does that happen? What's happening? Does that rock eventually turn into soil? Well, the short answer is yes. That's where soils come from, weathered rocks. And I can say that with some certainty because that's my PhD is in soil science. But even air, right? The air you breathe is a mixture of substances that are essential to chemical reactions that take place in your body. Most of it's nitrogen, 78% is nitrogen, but 20%, 21% is oxygen, and you have to have oxygen. Now, if you're a plant, oxygen is a waste product, right? They take in carbon dioxide, you know, that evil carbon dioxide that's destroying the planet. Right? I say that with tongue in cheek, of course. And anything that you observe, even man-made stuff like plastics, got there from chemical reactions. And some plastics are what we call biodegradable, and some are not. And you can find areas of the ocean that are garbage islands. Right? They're just strewn with plastics. Okay, let me move on. So what forms of energy are we interested in where chemical reactions occur? Well, if a chemical reaction occurs, maybe you feel some heat come off of it. It liberates heat. Or maybe it gets cold, right? If you work in a hospital setting, or if you've ever been in a hospital where a patient needed um, heat, localized heat on a particular thing, like a strained muscle, for instance. Then they'll grab this pack and they'll break a little capsule inside and mix it up, and it'll get hot. Right? Or they take another pack if you need cold, like you got a bad headache and you want to put a cold pack on your head. They'll take another pack and they'll break a capsule and mix it up, and it'll get cold. So instead of evolving heat, it absorbs heat. Right? Light. Some chemical reactions, some processes emit light or absorb light, one or the other. In fact, most of the information we have about the universe outside this planet, it comes to us on the horseback as light. Right? We point our telescopes at a distant star and take that light and run it through a spectrograph and split it up into its various colors, and it tells us something about that star. Right? In fact, the helium, let's see, there's our periodic table. Helium, the one on the far right up the right, was first discovered on the sun spectroscopically. Okay. Then later we found it on Earth too. It's not very common in the atmosphere because it's light, right? It just floats to the top and it's gone. Right? So question is, where do you get helium? Because we have stockpiles of helium still. We had, during World War I, we started using dirigibles, balloons for observation, and they were filled with helium. Well, most of the helium, the lion's share of the helium in the world was produced in the United States. So it was considered a strategic element. And we didn't let, for World War I, we didn't let the Germans have any. Right? So that's why the Hindenburg was filled with hydrogen instead of helium. And you know where that got them. Anyway, so helium is found in natural gas. Right? It's trapped underground in natural gas, so it can't escape. So when natural gas is drawn out of the earth, one of the processes of cleaning it up, besides removing all the dirt and water, is they separate out the helium and store it underground in abandoned salt mines, usually. I used to live in Louisiana, and underground there were places where there were salt domes, and usually they're associated with pockets of oil too. But sometimes they wanted the salt, like Avery Island. Everybody heard of Avery Island, where Tabasco sauce is made? Right, that's a salt dome. So they send hot water down there and they dissolve the salt, they bring it up and they use it to make Tabasco sauce. Well, when those salt domes get depleted of salt, right, they're just big underground caverns, they use those to store other things, like our strategic petroleum reserve, stored in abandoned salt domes, and helium is stored down there too. What you have to do is be sure that for the helium that it's not permeable, as you pump it down there and it disappears. Okay, so I'm talking too much about that. Let's go on. Let's see. I almost skipped that one. Matter comes, for our purposes, matter comes in 3 different states. Now, there are more than 3 states in the universe, but the conditions for those other states are extreme. So we're going to focus on solids, liquids, and gases, right? Everybody has sort of intuition about what these 3 forms are. Right? Solids have a definite shape, and they have a definite volume. So a solid you can set on the desk. There it is, right? It holds its own shape. It doesn't change its volume. Whereas a liquid will not hold its shape. It has a definite volume, but you have to put it in a container, and it'll assume the shape of the container, but it won't change its volume. Whereas gas, if you put a gas in a container, it better be sealed, right? Otherwise, it's all gone. It'll fill that container. So it has indefinite shape and indefinite volume. Those are the basic differences in the various states of matter. Now, when we write a chemical equation, if we want to specify what condition, what I hate it when that happens. My mind goes blank. And I just said the word a minute ago. State. What state is your reactant or product in? We use parenthetical things like G for gas, and L for liquid, and S for solid. Okay, so we put that right after the compound or the element to specify its condition, its state. There's one other one that we'll discuss later. It's AQ, which means aqueous. It's a solution. So those are the only ones you need to be familiar with. All right, we talked about this already, so I'm gonna skip those. Those are just examples. That one on the right is probably bromine. I think that's bromine. Say, wait a minute, bromine? No, bromine is a liquid. Chlorine, I bet that's chlorine. And there's an Eisenhower $50. Yep, that's a solid. I'm not sure what that green one is. Okay. So the state of matter, solid, liquid, or gas, depends on several factors. Temperature is one, probably one of the most important, right? If you take a solid and heat it up hot enough, it's going to melt, right, into a liquid. Heat it up even further and it'll turn it into a gas, assuming that the substance doesn't decompose from all the heat, right? If it doesn't decompose, then it'll go through solid, liquid, gas as you add heat. Pressure makes a difference also. If you have a gas and you put a lot of pressure on it, the first thing it'll do is heat up. So if you have a way of extracting that heat out of it, then as you pressurize it, eventually it'll condense into a liquid. And that's the basis for air conditioning. We take Freon or whatever is permitted these days, and you run it through a compressor, right? You put it under pressure, put the gas under pressure, and run it through the evaporator coils, through the condenser coils, and it gives off that heat. And you have a fan blowing and it sucks the heat away, right? So as long as you can get rid of that heat, and where'd that heat come from? Inside your house, right? That's the whole purpose of air conditioning, get rid of the heat. And then you take that condensed liquid and you run it back into the house in the evaporator coils, and you, through a valve, you let it, you release the pressure and run it through the coils, and it evaporates. And when it does, it cools and extracts heat from whatever's blowing over it, right? And that's the heat that comes from your house. So it goes through that cycle, and that is dependent largely upon pressure. The other determining factor in what state that you find matter in has to do with the strength of the forces that are holding those particles together. And we'll talk about that a little more later, but you can think of them, some of them as chemical bonds, right, holding elements together in compounds, or you can think of as intermolecular forces that are holding separate molecules together, which are significantly weaker. For instance, water. Right, what state is water at room temperature and pressure? It's a liquid. Yeah. Okay. Why is it a liquid? It's a liquid because it forms bonds, one water molecule with the other. And in order to get it to go from liquid to gas, you got to break those bonds. Now we'll try to explain why later. Right? This is a one semester survey course, so we can't get into too much detail. But those intermolecular forces also play a part in whether your substance is solid, liquid, or gas. All right. Now, when we define a property of matter, this is any distinguishing characteristic of that substance that identifies it as something separate from something else. It's unique, this property. Now, they may share properties with other substances, but if you have several properties identified and as a group, as a set, that makes this substance unique from any other. Now, those properties can either be physical properties or chemical properties. So we need to go a little further and define what we mean by that. Okay, a physical property is any characteristic that you observe without changing the identity of the substance. Something like your shirt is blue with a little red on it. Right? That's a physical property. I forgot to wear my deodorant today, so a physical property is my odor. Right? And I did use a deodorant today, don't worry. Plus, we're several feet apart. Physical state that we just discussed, that's a physical property. Melting point describes a physical property, a unique property of a substance, which is often used to characterize things. What's the melting point of this substance? What's the boiling point? How hard is it? Geologists like that one. They have a hardness scale. Right? Have everybody heard of the Mohs scale? It runs from 1 to 10. The softest material on that scale is 1, talc. The hardest one is a girl's best friend, right? A diamond. Those are natural substances. And if you're trying to characterize a mineral, its physical properties, how hard is it, then you try to scratch it, say, with a diamond, which is kind of stupid because there's nothing harder. So if you say scratch it with something in between, and you scratch it with two things, scratch it with this one, but you can't scratch it with that one, then it falls in between those two. Right? So that's a physical property, is hardness. Now, there are other scales. In fact, I knew a man who was an old timer, actually, in the steel industry, and they have a different system of hardness for steels. And he used to complain. He could take a hammer and wrap a piece of steel with it and get down there and even feel it, maybe even taste it, and tell you what kind of steel it was. And he said these young whippersnappers coming in here with their spectrometers and everything, and they still can't get it right. So I patiently listened to him and let him go on. So to measure the boiling point of a substance, a liquid must be changed into a gas, right? That's obvious. And when the phase change that occurs, we're talking physical change, right? We're going to get those in a minute, but the physical property is the boiling point. When it changes from one phase to another, the temperature is stable as long as you have both forms of matter together. Like, for instance, if you have ice and water together, you've got solid ice, you've got water, and they're at equilibrium, then that temperature will not change from 0 degrees Celsius until all the ice is gone. Right? It's stable. So why is the boiling point considered a physical property when a gas's appearance is much different from that of the liquid? The key word here is identity. Right? The gas identity, the molecule or the element that makes up the gas is exactly the same one that makes up the liquid. Its identity didn't change. Right? That's a physical property. That's why it's a physical property. All right. A chemical property describes something about a substance that relates to this change in identity. We're not talking about the actual change. It's just potential to change. So when we say sodium metal is very reactive in water, have you ever dropped a piece of sodium in water? Potassium works good too, right? It reacts violently. It gives off massive amounts of heat. It produces hydrogen gas as a product. And with all that heat and hydrogen gas, all you need is oxygen, and you got a flame. So if you drop some, say, a piece of potassium in a beaker of water, eventually you'll see a little flame coming up top where the gas bubbles up. Also, if you put a big enough piece in water, the reaction is so violent that it'll explode underwater and produce a shock wave. So if your neighbor's dog is peeing on your rose bushes and he's got a swimming pool, all you need is a big chunk of potassium, throw it in his pool and crack the bottom. Now, I didn't tell you to do that. Things like, have you ever seen a copper roof on a building? Okay. If it's brand new, it's like shiny, that shiny penny color. But gradually, it gets what's called a patina. And that's from chemical reactions with copper and things in the atmosphere, carbon dioxide, sulfur primarily. And it produces a kind of a greenish color. I'm sorry?
Like the Statue of Liberty.
Yeah. Yeah. Right. I've said before, I lived in Louisiana. Well, I did my master's degree and my PhD on LSU, at LSU. And we had a place called the Coliseum. And it was a place where we had an agricultural coliseum, not the sports coliseum. And it had a dirt arena, and the roof was covered in copper. And they replaced it while I was there, and it was bright, shiny penny color. And it didn't take long, say a month, 2 months, and that shine was gone. And initially, it was kind of dull and ugly, but over time, it got that green color, and it's nice. Okay, that's a chemical property of copper, is that it can turn green in air. Right? We're not saying it does. It just has that potential. That's a chemical property. Decomposition of organic matter in the soil. Right? So I took a whole course on that as part of my PhD requirements. And we studied the progression of decomposition in soil because we wanted to know where the organic matter comes from. Because organic matter is an essential part of soil. If you've got soils with low organic matter, they're not going to be very productive. Right? About the only thing you can grow in there is pine trees. The word is that pine trees will grow in marbles and water. Anyway, we studied decomposition, and that's a chemical property of any of those organic substances. Is they decompose in either an aerobic atmosphere or an anaerobic. Right? The processes are different. So I took another course in marine science, and we studied anaerobic decomposition. So that's important when you're trying to grow rice, because rice is in a flooded soil, right? So go down deep enough, the soils become anaerobic. And there's a cycle that occurs between the anaerobic layer and the aerobic layer. And if you put a certain type of nitrogen on that soil, it's gone, right? The plant can't get it. So you need to be particular about the type of nitrogen you put in the soil. You don't want to put nitrates because they'll denitrify into nitrogen and they're gone. Plant never sees them. So you put ammonia type compounds like ammonium sulfate, or urea is a good one, right? It's cheap and high analysis is like 46% nitrogen in urea. So that's a really concentrated source. Okay. Oh, there's your Statue of Liberty right there. So it's got that pretty green color. Classify each one of the following as a physical or a chemical property. Let's see. Iron metal rusts in an atmosphere of moist air. Chemical, yeah, right. Let's see. Do I have that one animated? Yeah, there it is. Mercury metal is a liquid at room temperature. That's physical. Oh, yeah, physical. In fact, mercury and bromine are the only two elements on the table that are liquids at room temperature. Okay. Let's see. I think we get to that. Get to that in the. Hold on a second. Yeah. Oh, the reason it threw me is we're all out of the periodic table, extra credit, right? So when you fill out the periodic table, it's going to ask you to identify solids, liquids, and gases under standard conditions. Right? So I gave you an answer to one of the problems. Now, the temptation is to say, if you look it up, if you Google it, to say gallium is a liquid, not at room temperature. If you put a piece of gallium in your hand, it'll melt. Right? It has a very low melting point. But at room temperature and pressure, gallium is a solid. Nickel metal dissolves in acid to produce a light green solution. Ooh, that's a tricky one there. What's happening? Well, we noticed a change in color. Probably chemical. You reckon? Yeah, that's a chemical property. It has to do with coordination chemistry. As the nickel goes into solution, it gathers around it so many water molecules and changes its electronic behavior. So it makes it absorb light at different wavelengths. That's the short answer. All right. Now we talk about changes. This is talking about the process of change, a physical change. And it changes only its appearance. It doesn't change its chemical composition. It doesn't change its identity. All right. So when we say, if we were to say water boils at 100 degrees centigrade, that's a chemical property. But if we describe water as boiling, the water is boiling, we're describing a physical change. Okay? Or water is freezing under conditions, let's say in winter months here. That's a physical change. It's changing a state. Chemical change is similarly, now we're not talking about the potential, we're talking about the actual reaction. So we leave iron out in the open, or leave a farm implement out in the field and abandon it. Over time, it'll rust. The rusting process is a chemical change. I grew up in Atlanta, and everybody remember the, let's see, what sports team was it? We had this place called the Omni, and the Atlanta Hawks played there, and the Atlanta, was the Flame, the hockey team, they played there too. I don't hold me to that, because I never went to one of those. I did go see the Globetrotters one time. They were a riot. Anyway, they built this special place called the Omni, and some architect got the bright idea, you know, if we cover this building with a special kind of steel that's designed to rust really fast, then what happens is, theoretically, is the rust, the iron oxide that forms on the surface, blocks out any further intrusion of water and oxygen and stops it from rusting. Okay. Now that's true for galvanized metals, right, where you dip a steel bucket in a molten zinc, you cover it in zinc, then the zinc oxidizes really fast and forms that kind of a I don't know, chalky surface. That's the zinc oxide, and that seals the surface. Or stainless steel, which is originally it was 35% chromium. Now they have different forms, but the idea is that chromium is more reactive than iron. So if you get a scratch on the surface of stainless steel, the reaction is so fast it seals that scratch with chromium oxide. Okay, and eliminates any further water and air intrusion. Right? So it stays unrusted. Well, back to my story. They went ahead and built the building. This architect, they provided them with the steel, and they covered the building with that steel, and sure enough, it rusted just like that, almost overnight, and sealed it. But Atlanta gets, I don't know, 45 inches of rain a year, probably. And all they needed was one good rainstorm, and you had red streaks across the concrete. They didn't realize, some bright architect didn't realize that when iron rusts, the contact between the iron oxide and the iron the steel underneath is very tenuous. Right? There's a change in density. Right, the iron oxide expands. That's why when you see a metal implement in the field that's rusted, it kind of comes off in flakes, right? Because the rusting part is less dense. It expands. So it expands away from the metal and allows more intrusion of water and oxygen underneath. Okay. So they put up with it for a while. They tried scrubbing the concrete, and that didn't work because it was a good stain. And it got to be so ugly, they tore the building down. That's the only solution to that problem. Okay. So let's see. How much time do I have? All right. Okay. So this is sort of a flow diagram. I put it in here for those who like to use flow diagrams. But it's not something you have to regurgitate. It's just a helpful device. Chemical and physical properties versus changes. So which of the following is an example of a chemical change? Right? Pulverizing rock salt? No, that's a physical change, right? Burning wood, right? You're taking cellulose, primarily cellulose, and maybe some lignin, and you're incorporating oxygen from the air, and it's changing into carbon dioxide and water and ash. Right? So you get a change in identity of the substances as a consequence. That's a burning of wood is chemical change. How about dissolving sugar in water? That's a physical change. Oops. In fact, the only chemical change there is burning wood. Melting a popsicle, right, is just changing phase. All right. Now let's talk about, stick to the physical. And we have to identify, for purposes of defining a mixture, we have to define what a pure substance is first. A pure substance is, for lack of better words, a single kind of matter. It cannot be separated into other kinds of matter by physical means. Now, chemical means, yeah, we can do some damage to it, but physical means, no. So what do we mean by physical means? Well, let's see. If it's a solution, it's not a pure substance, right? It's got at least a solvent and a solute in it, right? And you can separate those by physical means, say salt water. All you have to do is evaporate the water and you get the salt back. And if you condense the vapor coming off of it, you can get the water back too. That's the principle behind distillation. Every moonshiner knows that by heart. So a pure substance cannot be reduced any further by physical means. So things like gold bullion at 99.999% purity, we would consider that a pure substance. Or water, distilled water, we would consider that pure substance. So mixtures are combinations, physical combinations of pure substances, at least two, and there can be lots more. The defining characteristic of a mixture is that each of the components of the mixture retain their identity, their chemical identity. They can be separated by physical means, and then you can investigate their chemical identity as pure substances. But in the mixture, we didn't change them, right? It's still water and salt, or water and sugar if you're making a hummingbird feeder. All right, so that's a mixture. So we can characterize mixtures as either homogeneous, in which the dissolved substance is uniformly distributed throughout, right? Any place you sample that mixture, you're going to get the same composition, percent composition of the components, right? That's a uniform homogeneous mixture. Whereas heterogeneous mixtures are obviously not uniform, right? You sample them anywhere and you get a different ratio composition of the pure substances. If you put sand in water and stir it up, right, we're going to do that. We're going to put sand, salt in water and stir them up. So guess what happens? Well, the sand in water constitutes a heterogeneous mixture, because once you stop stirring, it starts to settle and you get a different composition. But the salt that you put in there goes into solution and it forms a homogeneous mixture, also known as a solution. Okay, so there's another flow diagram for classification. Which of the following is a homogeneous mixture? Okay, this speaks to the problem of answering a question by understanding what's being asked, right? If you're presented with a problem, first thing you want to know is what's the question. If you don't know the question, you'll never get the answer. So in this particular case, the best way to solve this, to answer this question, is to work backwards. Which ones of those are mixtures? If it's not a mixture, then it can't be homogeneous or heterogeneous, right? So we just throw it out. Pure water, that's not a mixture. Go down, copper metal, that's a pure substance. So we throw out A and E and work on B, C, and D. So which one's homogeneous? I'm sorry? Homogeneous. Gasoline is homogeneous. It's primarily octane, which is a hydrocarbon, and some other additives that the oil companies claim keep your engine clean. Or it probably has some ethanol in it too, right? By the way, if it weren't for government subsidies, ethanol as a fuel would be unviable. Right? Nobody could afford to produce it. It takes more energy to produce ethanol from corn than it does to that you get back from burning it. Right? So it's a no-win proposition. The only way that corn producers can sell their corn and make a profit with the ethanol producers is government subsidies. Anyway, let's get back to, so that's a homogeneous mixture. Gasoline, that's true, homogeneous. How about jelly beans? Jar of jelly beans. Now, all you have to do is look at those and you see maybe lots of reds on this side that everybody goes for. And then maybe lots of greens on this side. Lots of blacks that I don't care too much for. That's licorice. So they're heterogeneous. Soil, okay, I can speak with authority on this one. Soil is heterogeneous. Right? Have you ever seen a road cut? Not the kind that goes through rock, but the kind that goes through soil. Right? There are not that many of them in West Virginia. Most of our road cuts go through solid rock. But if you can ever find one that goes through soil and it's still exposed on the side, you can see layering, right? So that soil is heterogeneous. Okay, so the only homogeneous one in here is gasoline. Which one of these combinations has only pure substances? Right. So we look at each one. Oxygen is pure. Tap water, no, tap water's got dissolved solids in it, right? In some places in West Virginia, it's got calcium and magnesium. It's hard water. There are not many places that I think have soft water. Can you think of any? I can't think of any offhand. Some of them have dissolved sulfur, sulfur dioxide, or hydrogen sulfide. It's even worse, right? Stinkies, like white sulfur springs, green sulfur springs. Right? They got their name from the stink. How about a glass of tea? That's not a pure substance, right? That's got caffeine in it. It's got other dissolved oils. It's not suspended oils, and it's got water. So that the only pure substance there is oxygen. How about the second one? Oxygen, glucose. Yeah, glucose is pure, right? Silver is pure, so B is our best answer. Okay. There's only one possible answer, then you can work your way down, and when you find the right answer, you can stop. Go on to the next question, say during the exam. If you got any squirrely ones down there, like 2 of the above, none of the above, all of the above, then you got to look at all of them and be sure that those oddballs at the bottom don't apply. That's the only problem with that type of multiple choice question. Okay, what's an element? Well, an element is a pure substance, right? It cannot be reduced any further by physical means. In fact, it cannot be broken down even by chemical means. Right? Try anything you want to on an element, and you cannot reduce it further into other pure substances by chemical or physical means. Now, if we jump outside of chemistry and go to physics, oh yeah, you can break elements apart in a nuclear reactor, right? Bombard them with neutrons, and you can make different. You can transmute, right? But we're not going there. What would be chemical means? Well, chemical reactions in which you combine certain reactive things, right, are not going to make elements, 2 or more elements from a single element. You can use electric current or heat, right? All you're going to do is change the state, or beams of light. So if you want examples of elements, there they are, right there on that periodic table. And in fact, we got names for all 118 of them now. Let's see. Here we go. Let's skip that. Compound. A compound is a combination of 2 or more elements. It is a pure substance, like water. It's a pure substance. But it can be broken down by chemical means. It can be broken down by physical means, right? But it can be broken down by chemical means. We can split hydrogen and oxygen apart of water by using an electric current. All we need is a direct electric current and maybe a touch of hydrochloric acid so that the current will flow. Because water, pure water, is an insulator. You can't get a low voltage current to go through it. The high voltage is a different story. What high voltage does is it ionizes the water, so now you can get a current through it. So I went to school with this girl. Actually, I was a teacher's kid, and I went to a private school. So all I had to do was pay for my uniform and books. And the other kids who weren't teachers' kids were rich, right? So they had cabins in the woods and beach houses and all that other fancy stuff. Well, this one girl was in their cabin up in North Georgia, and she was talking on the phone on a landline in those days. This is in the 70s. Right? Cell phones weren't too common. Talking on a landline, taking a bath in a thunderstorm, and a lightning strike hit the telephone wire, and down the wire, went through her, through the water into the ground, and she died. So water can conduct electricity if the voltage is high enough. And in that case, it was, right? What's a lightning strike volt? Right? It ranges from tens of thousands to hundreds of thousands of volts. Right? So that's enough to ionize the water. But for our purposes, water is an insulator, and you have to add something in it to allow the current flow in order to get that reaction to occur. And then you can split H2O into H2 and O2. That reminds me, on that periodic table where I want you to memorize those different element symbols, some of them have little blue boxes around them. You'll notice that. Those blue boxes denote diatomic elements. That means under standard conditions, room temperature and 1 atmosphere pressure, they exist as diatomic elements, like hydrogen. There are 2 hydrogen atoms attached to each other to form a molecule. Oxygen, nitrogen, fluorine, chlorine, bromine, iodine. Those are all diatomic. And those should have that blue box around them. And notice hydrogen's off by itself, right, to the left. And then the others are like an inverted L. They go like that. Okay. I need to point that out because if you are given a word problem that says react hydrogen, write the equation for the reaction of hydrogen plus oxygen yields water. And you write H plus O yields H2O, it'll never balance. It has to be H2 plus O2 yields H2O. So you have to know that those elements are diatomic in order to answer the question correctly. Okay. So distinguishing characteristics between compounds and mixtures. Well, it's based upon the identity, actually. Mixtures have a mixed identity. In other words, they have 2 or more substances in there that retain their individual chemical identities. Whereas a compound has its own identity that's separate from the elements of which it is composed. Okay. And mixtures can be separated by physical means, compounds cannot. You need chemical methods to separate the parts of a compound. All right. So there's another flow chart. You're welcome to check it out, follow it through. So when we're classifying a sample of matter, we ask ourselves these questions. Does the sample of matter have the same properties throughout? Well, we also want to know, is it a pure substance or a mixture? If it doesn't have the same properties throughout, then it's got to be a mixture. Right? If it's a pure substance, then it's going to have the same properties by definition. If it's a mixture, then we got to decide with these 2 or more substances, is it heterogeneous or homogeneous for classification purposes? And then, can we break this substance down into simpler substances? If it's a pure substance, we need chemical means to do it. If it's a mixture, we only need physical means. Okay, those are questions you ask yourself when you're trying to classify matter. I'm not going to spend time on that one. Let's talk about, let me see. So that's the advantage of paying attention to the handouts. You can see where I'm supposed to be heading. Let's talk about the elements now. That's not going to work. That's not going to work either. Those guys are dead soldiers. Get out a fresh one. Oops. Huh. Oh, that's not metal. I got a magnet in my eraser, but it won't stick to this because it's not metal. It's not ferromagnetic, let's put it that way. Okay, elements, right? Periodic table is your best friend. In other words, hopefully over the course of this semester, we're going to learn how to use more and more and more information from the periodic table. It's chock full. Its design gives you information about the elements. In addition to the little squares for each element, there's information in there too. But the way it's laid out gives you massive amounts of information about the elements that you're interested in. 118 known elements, right? The heaviest ones are man-made, obviously. About 88 occur naturally. That number's probably gone up a little bit. 30 of them have been synthesized. The reason I say that is that over time, our analytical techniques become more and more refined and are able to detect smaller amounts of elements in nature. So some of those that were originally man-made and first identified as man-made, now we can find them in nature. They're just not very common. Atom percent. What do we mean by atom percent? Well, percent, what does percent mean? Parts per 100, right? Parts per 100 parts, right? So it's a dimensionless number. It could be mass per volume. It could be mass per mass. It could be volume per volume, right? That's why percent is dangerous. When we're using percent, we need to define the terms. And in this case, we're saying percent atoms per total, right? So for how many atoms are there in 100 total atoms in the sample? That's what that means. So out of 100 atoms, 91 of them are hydrogen. And this is in the whole universe. So why is hydrogen so abundant? Right? Isn't most of space empty? Stars, right? Stars. And that's typically the ratio of hydrogen to helium in a star is about 91 to 9, or about 10 to 1. Right? All the others are less than 0.1% in the universe as a whole. Now, when you get down to the Earth's crust, and that's just that very thin layer that covers the Earth, right? We're not going down into the mantle. We're not going down into the core. Actually, there are two cores. There's an outer core and an inner core. We're just the crust, right? The part that we can reach and sample, either on the surface, or we can dig mines, or we can drill down and take samples. The most abundant element by atom percent is oxygen. Right? Why oxygen? Because there are very few pure elements. Right? You can find gold in flakes and nuggets. Right? You have to go to Alaska and Canada, I think, if you want to do it that way. But most elements are compounds with oxygen. They're oxides. So there's lots of oxygen tied up in the Earth's crust. The next most common is silicon. Right? Think of what rocks are made of, what beach sand is, what the ocean floors are made of, is silicon dioxide. It's a major component. And aluminum is very common also. It's about 6%. So when I studied soils, we are taught, and our experimentation showed that most soils are some form of aluminosilicates, right? A combination of aluminum and silicon and oxygen, with some other things thrown in, but minor components. hydrogen is not all that common in the Earth's crust. And it goes down from there. So the most abundant is oxygen, next to silicon, and third is aluminum. Now, you can find concentrations because the Earth's crust is heterogeneous. You can find concentrations of things like iron deposits, iron oxide, in various places around the world, and use that to produce pure iron by chemical means. Right? You can find deposits of aluminum oxide. Right? They call it bauxite. Actually, bauxite is the ore. Aluminum oxide is what they purify from it. And then you send it to Alcoa in Pennsylvania, and they electrolyze it and get the aluminum out. Aluminum used to be more expensive than gold, like back in the 1600s, because the only way they knew to get it pure was by chemical means, and it was very tedious, difficult. But when the electrolysis process came along, you can make aluminum cheap enough you could wrap your food in it and throw it away. Anyway, which of the two elements dominate the Earth's crust, and which one element dominates the universe? So the Earth's crust is oxygen first, silicon second, right? And the universe is hydrogen. So that means it's that first one. Okay. Chemical symbols, right? I mentioned this one earlier. Chemical symbols are used to represent the elements. It makes more sense when we write elements and compounds and we devise chemical sentences, chemical reactions, that we use abbreviations, these symbols, so that we can put a lot of information in a small piece of paper. So you need to know these symbols. The chemical symbols are the alphabet of chemistry. You can't build any sentences, any words, any sentences, any compounds, any reactions without knowing those symbols. So if I throw PB up here, you know instantly it's lead. Right? Now, that's not derived from LEAD, right? So why is that PB and not LD? Because it's derived from the Latin. Right? Some of the element symbols are derived from the Latin words for lead. And lead in Latin is plumbum, which means heavy. Right? So that makes sense. Lead's heavy, so we call it plumbum. There are others, right? Like gold. The Latin for that is aurum. Or silver. Ag is argentum. Right. Those are just a few. There are several others. A great many of them are derived, can be associated with the English words. Right? So that makes those easy. But a few of them that you have to determine, like iron, for instance, right? It's ferrum, Latin ferrum for iron. K for potassium is calcium. Okay, non-English names, those are examples, and we'll skip over those. So when you write a two-letter symbol for an element, it has to be capital, small, always. All right, now let's talk about atoms. Because elements are composed of atoms. We physically separate a pure element by, say, halving it. If I can have it, physically have it. Eventually you get down to two, have it, you got one atom. It's still the element, but there's only one atom of it. The atom is the smallest particle of the element that can exist and still have the same properties of the element. It takes a lot of atoms to make an inch. Right? 254 million atoms, roughly speaking, would lined up make an inch. So they're very, very small. A molecule is a compound of atoms in which their association, their bonding together, creates a unique substance with different properties, chemical properties, than the elements. Plus, they behave as a single unit. Water is an example. Carbon dioxide is another example of a molecule. Now, you can have elemental molecules too, like the diatomics, 2 oxygens, 2 hydrogens. Those are molecules. They're a combination of elements bound together by chemical bonds in which they function as a single unit. Now, why am I emphasizing that so much? Because when we combine some other elements to make compounds, they're not molecular, right? Is that's on a subsequent slide? Let me see. No, I need to make that distinction now. So, whereas a molecule binds the elements together so strongly that they behave as a single unit in association with each other or with other substances. Whereas molecule, this is a type of compound. Right? Compound is just an association of elements. Molecule, then you have ionic compounds. Oops. In this case, the individual ions are attracted to one another. The positives and the negatives are attracted by Coulombic forces, simple electrostatic attraction. But they don't form unique individual molecules. Sodium chloride is a good example, right? In sodium chloride, you have positives and negatives. Right? This is the simplest whole number ratio of sodium and chlorine in a little cube of salt. Right? You ever spill salt on the table and look at it with a magnifying glass? Yeah, it's a cube. Thank you. I was beginning to think, with my other classes, I was beginning to think I was the only one that did that kind of stuff. Yeah, take out a magnifying glass and look at it. They're all little cubes. So they're cubes because this sodium is surrounded by chlorines or chloride ions, right? In behind and in front. And this chloride is surrounded by sodium. And that goes on and on and on and on, as big as the cube is. So rather than say sodium 10 to the 6th and chlorine 10 to the 6th for that cube, right? We use the simplest whole number ratio, which is 1 to 1. So ionic compounds are not molecular. Right? The ions are still independent but attracted to one another. So back to molecules now. We can describe molecules as diatomic, which we did for those elements, right? But you could have diatomics like, well, let's see, carbon monoxide, 1 carbon, 1 oxygen. That's diatomic. It's got 2 atoms. Triatomic would be, you could use the same elements, only now you got 2 oxygens. So you have 3 atoms in that molecule. Carbon dioxide versus carbon monoxide. They have different identities. Yeah.
One is a lot more dangerous than the other.
Yes, it is. Right? Anybody know how carbon monoxide kills you? Silently? Yeah, that's true. That is true. What carbon monoxide does, I'm sorry?
The way that it bonds.
Yes. It attaches itself to the iron in your hemoglobin and will not turn loose. So you suffocate on a molecular level, right? There's no way to carry oxygen to your tissues because it's all bound with carbon monoxide. Hopefully, we'll get when we start building molecules and learning how to structure them and assign electrons where they're going, then it might become obvious the difference in the structures here, why carbon monoxide is so dangerous. Okay, another way, diatomic, triatomic, another way to describe a molecule is whether the molecule is made up of the same element. So that chlorine, phosphorus, sulfur, they have different numbers of atoms. So chlorine would be diatomic, phosphorus would be tetratomic, sulfur would be hexatomic, because there's 6 of them. We use the Greek prefixes. Mono, di, tri, tetra, penta, hexa, hepta for 7, octa for 8, nona for 9, and deca for 10. Those prefixes tell you how many of something there is. But they're all the same element for each of those examples. So they're homoatomic. So phosphorus would be tetraatomic, homoatomic. Heteroatomic, you would have different elements. These are both heteroatomic, carbon and oxygen. Oops. There we go. All right, so those are examples. If we have A and B are different elements, the first one, A, is diatomic. Second one's triatomic, tetraatomic, and this one's tetraatomic too. But they're all heteroatomic because they're made up of at least 2 different elements. Okay, classify, what's Xe? I'm sorry? Xenon, yeah, xenon, right? It's a noble gas. That's what's strange about this, right? Noble gases are not, they're supposed to be inert. Right? But those bigger ones, xenon is way down, it's huge. They can be forced to form compounds. They usually do it with halogens because they're more reactive. But xenon tetrafluoride is what? Diatomic or triatomic or what? Ditri. 4 plus 1 is 5. It's pentatomic, isn't it? Yep. Is it homo or heteroatomic? Right? Heteroatomic. And is it element or compound? Compound, yeah. Okay. Let's see. Right, here's one where you have all of these, so we have to look at each one. Okay. If you find one that's false, then D has to be false because they can't all be true and one be false. So the smallest particle of an element that can exist and still have properties of the element is called an atom. That's true? Yeah, that's true. So the first one's true. How about a group of 2 or more atoms that function as a unit form a molecule? Yep, that's a good one. Some classifications of molecules are diatomic, homoatomic, and heteroatomic. Yeah, they're all true. Okay. Okay, so when we combine elements into compounds, whether they're molecular or ionic, it doesn't matter. When you write their formulas, we need a method to write them. So I'm not sure if if there's a slide on this. I don't want to steal my own thunder. Doesn't look like there is. When we write a symbol, a chemical symbol, I'm going to use X as our symbol because there's nothing on the periodic table that's just X. There are 4 positions here that are reserved for information. This one, this position here in the upper right-hand corner is reserved for charge. If there's nothing there, then it's neutral. Or you can write a 0 in, but it's neutral. Or it could be +1, +2, +3, -1, -2, -3, whatever. That makes it an ion if it actually has a value. Okay. This position over here is the number of atoms. Right. So for hydrogen gas, it'd be H2. There are 2 hydrogens. Or H2O would be 2 hydrogens and 1 oxygen. If there's just 1, we don't write it in. Because if you write the symbol, how many do you have to have minimum? 1, right? Okay. When we write element symbols, compounds, we're trying to put this whole system together. And later, you'll see when we try to name compounds, we try to do so in an unambiguous way. That is, whatever we do, can only be interpreted one way. And we don't want to be redundant. So writing a 1 in there would be redundant. You got the symbol, there's one of them. You don't need to write 1. Okay, on this side is designated by Z. This is the number of protons in the atom, in the nucleus. Number of protons. That's also called the atomic number. Okay. This position is reserved, and you won't always see these values in there unless the discussion is about the nucleus of the atom, right? Most chemical reactions are written, compounds are written, elements written, reactions are written without these values in there because they don't make a difference to the chemistry. If you've got the symbol, you know what this is because the number of protons is unique for every element. If you change the number of protons, you change the element. Okay. Now this one though can vary within an element, right? Because this is the number of protons. This is the number of protons plus the number of neutrons. So if you get a different number of neutrons, you still have the same number of protons, so it's the same element. But it's a different mass for the atom because you have more or less number of protons, neutrons. So what do we call that? I'm probably stealing my own thunder for later. That's an isotope. Okay. It has the same chemical properties as any of its neighbors of different isotopes, but it has a different number of neutrons. So this is the mass number. And it's always a digit, whole numbers. Okay. As opposed to atomic mass, which is on the chart, and most of those you'll see as decimals. Right? Let's see. An example: lithium 6.941. It's related to this value, but it's a weighted average of all the isotopes in nature. So that's why it comes out as a fraction. It's kind of like averaging your grades, right? Grade point average, right? A course that has 3 credit hours and you make an A in it, that's like 21. Right? Am I doing that right? No. 3 hours. 3 times 4 is 12. And then that goes into calculating your grade point average, right? So a class that only has 1 credit hour, the grade has less weight. Right? So we use that concept in atomic weight. Okay. So when we write compounds, we already written water. So let's try this other one, calcium phosphate. Right, I'm going to throw a lot at you at once. When we say 3 there, that means in that, and this is an ionic compound. So this is the simplest whole number ratio of the parts. This behaves as a single unit. This behaves as a single unit. It's called a polyatomic ion. And we need 2 of those. Right? So this subscript can be either next to an element or it can be in a parentheses. And the reason we have to do that is because this PO4 behaves as a single unit. And we can't break it apart. We can't change the subscripts. So if we need more than 1, then we have to put parentheses and put a subscript on the outside of the parentheses. But this means that there are 3 calciums, right? So how many atoms are in here total? All right, 3 calciums, right? 2 of those whole units, so we have 2 phosphorus, right? Okay. 4 oxygen in that unit, but we got 2 of them. So that's 8, right? So that equals 13. So there are 13 atoms in that formula. And very often for ionic compounds, rather than say molecular, we say formula unit to distinguish it from molecular. All right, so that's what the subscripts do. They tell us how many of what's in there. We'll talk a little bit more about when we name compounds. We'll get into polyatomic ions a little in depth. How many atoms are in each one of these? Well, H2SO4 is sulfuric acid. So that's 2 plus 1 is 3 plus 4 is 7. Right? And then iron carbonate, actually that's iron 3 carbonate, properly named, has 2 irons, 3 carbons, and 9 oxygens. Okay. Looks like we're coming to the end of chapter 1. And let's see. An electrical current is applied to 50 milliliters of water after a period of time. There's nothing left in the container because what? If we apply an electrical current to water and there's nothing left, what happened to it? It's possible. An electrical current could heat it and evaporate it. But it may also be possible that we have split the water into hydrogen and oxygen and they evaporated. Right? So they're not really giving you enough information here. They probably should have said 50 milliliters of water with a smidgen of acid in it to make it conductive. And then you could assume that you're electrolyzing water into hydrogen and oxygen. So that's what they're expecting with this question. A chemical change is taking place. No residue is left because the water is pure. I'm going to skip this one because we're running out of time. So, chapter 2. In the sciences, obviously including chemistry, measurements are ultimately something that you're going to have to do. If you're going to run any type of experiment, you got to make a measurement of some kind. Sometimes the measurements are numerical, right? You get numbers. Sometimes they're observational. So we're going to talk about when you make a measurement, 99% of the time you're going to have a number and a unit. Without the unit, the number doesn't mean anything. Like I could say I'm 70 and you might assume that I'm 70 years old, right? Which would be a correct assumption, but maybe I mean that I'm 70 inches tall, but I didn't say that, right? So 70 doesn't mean anything unless you have a unit with it. The measurement may be used to determine some dimensions, right? Maybe a change in dimensions of some kind. The capacity of a vessel, the units might be identified in milliliters, which is a measure of volume. Or a quantity, if you count something, count numbers of things. That might be a pure number, right? If you're just counting numbers. But you can have units of measure for numbers of things too, like we're going to learn later, the mole is a unit of usually atoms or ions or molecules. And a mole is equivalent to a very large number of things. Right? We'll get to that later. So types of measurements, you could measure mass, which is a measure of amount of something that's there, right? It's something that does not change no matter where you are in the universe. Once you identify the mass as so many units of this substance, then it'll be that way no matter where you are in the universe, except maybe in relativistic situations like near black holes. Then it changes slightly. But you can measure mass, you can measure volume, right, with the calibrated devices. You can measure lengths, right, with, well, this is yardstick. That's English system. We need metrics. Meter stick around here somewhere. Time, you measure time, right? So many seconds, so many minutes, so many hours, days, however many the units are. You can measure, my goodness, you were hungry, huh? Temperature. We need a system for measuring temperature, right? In this country, everybody's familiar with Fahrenheit, which is how the weather is reported. But in the sciences, we use Celsius. It's a different system. Pressure. Weathermen will report pressure in millibars. We'll study pressure in terms of atmospheres. But you can use also millimeters of mercury, right? And when your blood pressure is taken, the unit of pressure is millimeters of mercury. Like, so if it's 120/80, it's 120 millimeters of mercury systolic, yeah, and 80 millimeters diastolic. And concentrations, units of measure that tell us how much of something is in something else, concentration units. I mentioned the English system with some disdain a minute ago. It's primarily used in this country only. Everywhere else in the world, they use the metric system for everything. In this system, we're sort of schizophrenic. We use the English system for common measures, and then for the sciences, we use the metric system. So the problem with the English system is that the units of measure and the conversions between units of measure are arbitrary, right? The inch is like, I don't know, like 2 fingers wide, or the foot used to be, how long is the king's foot? So that measure would change every time you got a new king. The pound, right? I don't know offhand where it came from. Quarts and gallons. So you have to measure, you have to know the conversion factors for each one, like 4 quarts in a gallon, 2 pints in a quart, 2 cups in a pint, so forth, 8 ounces in a cup, that type of thing. Whereas the metric system is all decimals, right? So if you've got a unit here, and you are going to use only 1/10 of it, then maybe that you can make that a different unit. But all you need is to express that 1/10 as a prefix to the value. So 1/10 of a meter is a decimeter, which deci means 1/10 of. So everything is by changes in tenths. Much more convenient to use. So scientific work uses the metric system. Now, in the metric system, we have base units. That is the unit of measure that stands alone. And if we change that unit of measure, we have to put a prefix in front of it to say, how have we changed it? So if we have, okay, we measured something in meters. The abbreviation, the symbol for that is m, little m. But we want to drive a long distance. We don't want to say so many meters, like what is it? Foot races are 1,500 meters in metric system is a lot, a moderate distance. But sometimes you have people that are, we got any marathoners in here? You'll do a 5K or a 10K run, right? That means kilometers. But K means 1,000 times a meter. So the unit of measure here is bigger. So if we say that we're going to do a 1,500 meter run, right? But we want to put that in kilometers, what would that be? 1.5 kilometers, right? 1.5 kilometers. Notice that these represent the same distance. Right? They're just different units of measure, but it's the same distance. And when the unit of measure gets bigger, meters gets bigger to kilometers, the number associated with it gets smaller. It always does that. These prefixes that we use, let me see. Is there a slide for that? Yeah. The prefixes have meanings. They're multipliers, or actually fractional multipliers in some cases. So we need the base unit. We need to decide what the base unit is. And scientists have to agree upon what that means. When we say a gram, what does that mean? How do we standardize it? Well, as it turns out, the base unit of a gram is not the standard unit. The International System, or SI, System International, so it's French, right? They do everything backwards. The base unit for mass is the kilogram. Not the base unit, excuse me, the fundamental unit. This is the defining unit, the kilogram. So there's a platinum iridium cylinder in a double bell jar filled with argon in some cave in France. And that's the standard kilogram, right? So if you want to standardize your kilogram, you got to compare it to that one. You send them your kilogram, they'll compare it, send it back to you with a report and say, this is not exactly a kilogram, right? It's 1.000002 kilograms. So in this case, the base unit is the gram, but it's not the fundamental unit. The fundamental unit is the kilogram. And if you think about it for a minute, that makes sense. Because what do you not want on your standard? You don't want any adulteration. You don't want fingerprints. You don't want scratches. Right? You don't want corrosion. So if any of those things happen to a little bitty gram, a percentage error is huge. So we inherited the gram from medieval times, so we had to accept it and just go up to a kilogram for something bigger that would tolerate corrosion, scratches, and things like that more readily. So these fundamental units for mass is kilogram, for length is the meter. Okay. For time is the second. Right? We inherited the second from ancient time. So all we had to do was just standardize it. Right? Now we use what they call atomic clocks. They use the radioactive decay of a certain nuclide, and they measure that decay over time, and that sets the standard for the second. Right? They have several of those stationed around the world, and in fact, when I was younger, I was into astronomy, and we had a radio with a time signal on it. It would beep like that. So when we were watching for things like meteor showers, we could say it went from this direction to that direction, and we knew our constellations. We could say where it started, where it ended, and the time signature was right there, and so we should write it down. And it was tied to the atomic clock in Colorado, I think. So if we knew the direction it was moving and the exact time, then the researchers who were being blessed with our observations could do calculations on that meteor shower and do whatever else they wanted to with it. But the second was standardized at a certain value. Let's see, this is mass, length, time. Let me see, what else do we got? I know I'm missing something. Did I put it in here? Yeah, there it is. There's a separate slide. So hold that thought and we'll get to it. But these prefixes are used with the base unit. So in this case, the base unit is the same as the fundamental unit. But in this case, the fundamental unit is a multiple of the base unit. The base unit is gram. And kilo means 1,000 times. So the size of this unit is 1,000 times the gram. Right? The platinum iridium cylinder is about that big around, about that tall. And these are the other prefixes that we can use. Notice the difference between small m as a prefix. Like if the meter, then we put a little m in front of it, a little m. That's millimeter, right? 1,000th of a meter. Right? So the unit gets smaller. If we put a big M in front of it, that's megameter. right? And that's a million times a meter. I might use something like that in close astronomy, distance to a planet, or even further out, a big G, or gigameter, or a billionth of. Right? Anybody who's active in computers knows what those prefixes mean, right? In terms of megabytes, million bytes, gigabytes. Now we're up to terabytes, right? 10 to the 12th bytes. By the way, what's a byte? It's 8 bits, right? So when they say your speed, your internet speed is one. Let's see. I'm trying to remember what mine is. Mine's 1 gig at home. At home, one gigabit per second. Right? So that'd be 1 divided by 8 would be that many bytes per second. So we get those things confused. Okay, which I'm doing right now. So these prefixes modify the base unit. Centi means a hundredth of. So a centimeter is a hundredth of a meter. Right? So if a meter's this long, a centimeter is going to be about that big. So we develop, over time, you develop sort of an intuition of what they mean, just like you would with the English system. Micro is the Greek mu, right? Or for drug dispensing, I don't think they use this symbol. They use the MCG. For drugs would be microgram. They don't like Greek symbols in medicine. Nano, a billionth of, right? Anybody have any sportswear with nanotechnology in it? No. If you do, if you decide to buy something for exercise purposes and it has nanotechnology in it, those little pieces, fiber inputs that they put in there to modify the fiber, are about that size. They're a nanometer in length, or in that range. Picometers, that's more on the atomic scale, right? If we're looking at a crystal structure of a certain metal, right, we're going to use units of picometer. Okay, there's the base unit and the fundamental unit, meter in length. Originally, the meter was defined as a fraction of the distance from the North Pole to the equator through Greenwich, England, where the prime meridian, that's 0. So they took that length as best they could determine it and subdivided it into convenient, and that became the meter. And then they, to standardize it, they created a platinum meridian bar and said, okay, that's it. This is the meter. Everything else is based on that. They couldn't just use a plain old straight blocky bar because it would be susceptible to warping. So they had to create a design that wouldn't warp. So if you cross-section the meter, it looks more like this. Okay. Oops. There we go. They take that meter bar and cross section is like that, and it's a meter long, made out of platinum iridium, and they keep it in a inert atmosphere, just like the kilogram. Fortunately, though, now the meter is standardized based on the number of wavelengths of a certain emission, laser light emission. So if you've got enough money, you can buy an instrument that's calibrated to spit out a meter length using those parameters. So you don't have to compare your meter to the original bar. We haven't figured out how to do that with the kilogram yet. So you still have to go back to that one. So the gram is the base unit, kilogram is the fundamental unit, and we need to draw a distinction between mass and weight. Right? Mass is a measure of substance. How much substance is there? The mass tells you that. And it's the same no matter where you are. On the surface of the earth, on the surface of the moon, a kilogram is a kilogram. On the surface of the earth, I might weigh 200 pounds. On the surface of the moon, it'd be 1/6 of that. Right? Like maybe 32 or 33 pounds. That's the difference. Mass is amount of substance. Weight is a force. So the force that I'm exerting on the surface of the earth is based upon my mass, but it will change depending on the gravitational field. So if I tried that on what they call super planets, right? They found these planets, rocky planets around other stars, and they've determined that they're like 8-10 times as big as the Earth. They call them super Earths, right? So that would be I'd weigh quite a bit more on that surface, and probably wouldn't move as fast. The liter is the base unit of volume. But the liter itself, volume is not a fundamental unit. Volume is a derived unit from length. Right? It's the cube of the length. So the derived unit for would be based upon this fundamental unit, the meter. And the liter is not a cubic meter. Right? It's a fraction of that. It's actually 1,000 cubic centimeters. So a centimeter would be 100th of a meter. And then you would take, actually a decimeter, right? 1/10 of a meter would be the side of a liter. So you have decimeter, decimeter, decimeter. That would be a liter. So we get to the point where we kind of understand what a liter, what size is a liter, right? We have 2-liter bottles, so maybe half that size, or sometimes you buy drinks in liter bottles, right? They're about like that. So you get an intuition for what a liter looks like. In the lab, it'll be in a graduated cylinder, about that big around, and about that tall. About that tall. And then we derive units from that. Like a milliliter is 1,000th of a liter. And in fact, in case you're interested, 1 milliliter is equal exactly to 1 cubic centimeter. Right? So when you see, if you're in a hospital setting and you see something old in a storeroom, it's in cc's, right? Cubic centimeters. The modern preparation now will be in milliliters rather than cc's. They use cc's initially because they couldn't write cm cubed as easily on their labels, right? So they just said cc's abbreviation. But they could have just as easily used milliliters. I don't know why. Somebody decided to go one way rather than the other. Now it's milliliters. Should be. Are they old or young? Somewhat?
Some favorite TV shows.
Oh, okay. Yeah, you kind of have to take TV shows with a grain of salt. A big cube of salt. Okay. So length, mass, volume, we've covered those topics. Which of the following represents the largest measurement of mass of an object? A gram, a microgram, a nanogram, or a kilogram? Kilogram's the largest, yes. Okay, now we're going to talk about where I'm headed with this is when we are making a measurement and reporting the number, we have to agree as scientists upon what that number means and how trustworthy is it. Okay, so let me make some room here. say we measure something that's, I don't know, 7, 3, 4, 5, and we'll leave the units out because I'm talking about the number now. It could be any units. Scientists know, they're trained that, and this goes back to the concept of uncertainty. Anytime you make a measurement, the measurement as a whole carries with it a certain, pun intended, a certain amount of uncertainty. It might be 7.345, it might be 7.346, it might be 7.344. It could be in a range, right? And if you measure it several times, you may get different numbers. Or if you get 3 or 4 people to measure the same thing, they might get different measurements. So uncertainty is something we have to live with. So what we've decided is that when you report a number, these values here are considered certain. Right? They don't vary. This is the uncertain number right here. This is essentially a guess. Okay. When you're actually measuring something, how do you know which one is the guess? Well, for instance, if you have a graduated cylinder, right, and you have markings for the volume, but the liquid level maybe falls in between those, then these values are a certain value, the ones that have markings. The uncertain one is the guess in between. Okay, that's how you treat it as a practical matter. Okay. This slide is saying that there are different types of numbers, and some numbers we treat as exact numbers. And those are usually types where you have counting numbers, like some 9 pencils, right? You're not going to have half a pencil or a fraction of a pencil. Right? It either is a pencil or it's not a pencil. Those are exact numbers. There's no uncertainty associated with those. Simple fractions are considered exact numbers. Okay. Conversion factors, and we'll talk about those a little bit more. But when you identified a conversion factor, then that conversion factor is an exact number. It has no bearing on the calculation in terms of uncertainty. And that's where we're headed. We're trying to figure out, when we do a calculation with 2 or more numbers, how much confidence do we have in the answer? Okay, that's where we're headed. Let's see. So that discussion is on this slide: certain digits versus uncertain digits. The first uncertain digit is the last one in the line from left to right. And here's an example where the one on the left is 3.7 centimeters. So 0.7 is the uncertain digit and 3 is the certain digit. But if we have tenths available to us, then we find that we have 3.7, and then in between 0.7 and 0.8 is the hundredths value, which we estimate at 4. So in this one, the uncertain digit is 4, and the certain is 3 and 7. Okay, now we're talking about significant figures, right? Has everybody in here had algebra? Or at least math, right? We talk about significant figures in calculations. Good, so this will be kind of a review for most of you. Significant figures is a way that we use to track uncertainty so that we can predict the error, the uncertainty in our answers. So first of all, we need the rules for significant figures. Significant figures go by these rules. The first rule is the easy one. All non-zero digits are significant. So in this 3, 4, 5, 6, you have 4 significant figures. in that number. Okay. So where do we go from here? Zeros. You can have 3 places for zeros to appear. You can have zeros on the left, the far left of the number, like for this fraction, 0.048. Those left-hand zeros are never significant. Okay. So this number only has 2 significant figures in it. The next one is we move to the right. Suppose you have non-zero numbers with zeros in between them. Right. Those are confined or captive zeros. Those are always significant because they're essential placeholders. So this number has 4 significant figures in it. So obviously we're going to the far right. Right. If you have zeros on the far right, but they're hanging out there by themselves, when are they significant? They're only significant if there is an explicit decimal in the number somewhere. So 9.300, there's that decimal. Those zeros are significant. But if we wrote that number, say, without, it would be a different number, obviously. It's not 9.3. It's 9,300. But without the decimal, those 2 zeros are not significant. This only has 2 significant figures. But suppose we intended for them to be significant. In other words, certain, 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 uncertain. In order to keep them as significant, we have to put an explicit decimal there. Even though it's understood, right? An explicit decimal changes the nature of the zeros. Okay. Trailing zeros, that's what this slide is about. The difference between 150 and 150 point. All right. Let's see. I'm going to skip that one. We have to agree also on rounding, because if we've got an answer that our calculator says is this long, you obviously can't keep all of them. You got to round out to the significant figures that you're permitted in the answer. And we'll talk about that in a minute too. So when you do, we're just going to use the simplest way of rounding possible. All right. If it's less than 5, in this example, we're rounding to the 3.72 position. You look to the right, just 1 digit to the right. Is it less than 5? In this case, it is. So all those from 4 over drop and 2 stays the same. In other words, that's called rounding down. Round up in the next example, if you are rounding to 3 significant figures, 5.00, the next digit to the right is 6. It's greater than 5. It's 5 or greater. So you round the first 0 to its left to 1, and everything else drops. Okay. I don't think you guys are going to make the mistake, but you don't, in that first one, you don't round 7 rounds 6 up to 7, and 7 rounds 5 up to 6, and 6 rounds 4 up to 5, and 5 rounds 2 up to 3, right? You have a rounding error. We only go 1 to the right of the position we're rounding, and everything else is thrown out, is superfluous. Okay. All right. Now, operational rules. There are essentially 2 operational rules. One for multiply, divide, and one for add, subtract. Multiply, divide can also be considered powers of, because it's essentially a multiply, 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 however many the power is. So the rule works for that also. Multiply, divide is the simplest one. When you have 2 or more numbers that are multiplied together, all you have to do is look back at the original numbers and find the one with the least number of significant figures. In this case, 2.57 has 3. So your answer, the calculator gives you 15.51766. You want to round to 3 significant figures. You round to the least number of the operators. So 2.57 is 3. The answer can only have 3 significant figures. So we round the 5, the far right 5 position, to 5 because its neighbor is 1. And all those drop away. Now we have 3 significant figures in our answer. Okay. If you have a series of calculations that are all multiply and divide, right? There are no add, subtract in there. All multiply, divide. It's a good idea to do all the steps. Multiply, multiply, divide, divide, multiply, multiply, all of them. Get your final answer. Then go back and look at all of the operators and see which one's the least. Then round your answer. The reason that I do that is because if you multiply, round, divide, round, you can introduce significant rounding errors. Because what if each time you round up, 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 up? Then you've introduced a significant error in your answer. So if it's only multiply, divide, go through the whole thing, take the last one, and see which one of those has the least, and then apply it to your answer. And you eliminate the problem of rounding errors that way. Addition and subtraction is another animal altogether. If you've got add, subtract, then you have to follow the order of operation. Remember the acronym PEMDAS? Yeah. Right. If you have parentheses, that will dictate, which operations come first. But if you don't, then you do exponents first. Then you do multiplies, then you do divide, then you do add, then you do subtract. That's if you're left without guidance from parentheses. So how do you do it? Right. Well, with an add subtract rule, you line up the decimal points, even if they're understood. Right. In this case, they're explicit. But I'm going to show you an example in a minute where they're understood decimals. And what do you do then? Right. So that's coming. In this case, you've got 9.333 and 1.4, add them together. Right. So when you add them all together, you get 10.733. But you're restricted to the farthest, to the farthest left of the numbers. 1.4 dictates that you can only keep the 10th position in this addition, right? Because there's nothing past 4. The 0.4 is the uncertain digit, and that fixes the length of your answer at the 10th decimal place. Right, so you have to round to that one. And since to the right of 7 is 3, you throw the 3's out and you keep the 7, and the answer is 10.7. So the uncertain digit is in the 10th place as it was in the operators above. Okay. All right. So let me see. Did I put this one in? Yeah, try this one. 9333 and 1400. We have to assume decimal here, line up the decimals. Then we're going to add, right? Okay, so we add 3, 3, 7, 10. So which one is the uncertain digit that limits the length of your answer? That one right there, right? Right, because these are not significant. This is your uncertain digit. So we have to, let's see, we have to limit to that position. So 7, to the right of 7 is 3. We have 1, 0, 7, and we need placeholders. There we go. So our answer can only be 10,700 with no decimal. All right. See some circular nods. All right. Okay, if we have to do a series of or combined measurements, this happens sometimes in the lab. And you have to physically combine the values. In this case, we're going to combine 2 volumes. If we measure a volume in the left-hand cylinder and a volume in the right-hand cylinder, and we put them together, what can we claim as the volume for the final? Which one limits the accuracy of your measurement? I'm sorry? The one on the left, right? It's the least accurate measure because it's only calibrated to 0.2 of a milliliter, whereas the one on the right is calibrated to 0.02 of a milliliter. So we're limited by the one on the left. So if you add them together, let's see, it looks like they're sitting right on the line. So our final would, our additional digit would be a 0. So the first one would be 2.80 on the left milliliters, and the one on the right would be 0.280. All right, so if we add those together, by the way, if you've got a decimal here and there's no non-zero number out here, you better put a 0. We want a captive decimal. We don't want any orphan decimals in our numbers. All right. If you write it without that 0 in it, it's the wrong answer. Okay, 0, 8, 0, and 3, right? But we can only keep that much. So it's 3.08. Now let me see if my slide agrees with me. Some of these slides need to be updated. Yeah, 3.08. All right. Here, these are exact numbers again. And this references conversion factors. By convention, we allow conversion factors to be exact numbers. In other words, in a calculation, the conversion factor has no impact on the answer's significant figures. 2.54 centimeters per inch. Now I need to talk about conversion factors a little more, I think. And get that under our belt. I'm just looking ahead to see if I've got the discussion. Yeah, okay, good. So how do we get conversion factors? Why do we want conversion factors? Well, maybe we measure in one unit, but we want to express it in a different unit, right? It's still the same measurement, same phenomenon. For instance, length. If I'm measuring this length, I could do it in meters, I could do it in decimeters, I could do it in millimeters, but it's still the same length. So the conversion factor doesn't change the physical nature of the measurement. It only changes the expression of that value. So how do we do that? Well, let's see. I'm gonna skip that. Oh, I jumped not too far. Maybe I ought to. No, we'll come back. We need to talk about exponential versus scientific notation first. If you have very large numbers and you don't want to change the units of measure, then one way to shorten the answer is to use scientific notation. Now that we know what significant figures are and how to calculate those, then we can produce a notation that is accurate for those significant figures and still contains all the information in the big number. So there's a difference between exponential and scientific notation. Exponential notation simply means that you take a large number like, I don't know, miles. Anybody know what that is? The average distance of the sun from the Earth. 93 million miles. If it was in kilometers, it'd be about 150. But we want to put that in a smaller, a more compact form. Exponential notation simply says that we reduce part of a number into powers of 10. And then the coefficient of the number, what's left over, goes in a multiplier of the powers of 10. Right? So if we move the decimal 1, 2, 3, 4, 5, let's say 5 over like that, that would be 5 powers of 10. Right? And then what's left over is 930, isn't it? Right. That would be exponential notation. That represents this number. It's not scientific notation. Scientific notation is a subset of that and requires that the coefficient be between 1 and 10. Okay, so we would have to go a step further. 9.3 times 10, 2 more, be 7, right? That would be scientific notation. And now that we know the rules for significant, yeah.
So in what different situations would you use exponential versus scientific?
I would never.
Okay.
Yeah, I'm just drawing that distinction. So if you do see it out there, you'll know.
Okay.
Yeah, we would always use scientific notation.
Okay.
There's some textbooks that equate the two. You know, and I'm making a distinction here because it's important. Okay, so you can think of it in terms of information here is being stored up in powers of 10.
So there's no like real world situation where you use an over scientific.
On rare occasions, perhaps if you're using the same unit of measure in a table, you got this measurement, and you want to use the same unit of measure, but one of your answers is less than 1, then you may want to keep the powers the same and put it in as 0 point something.
Gotcha. Okay.
Yeah. Now that happens.
Thank you.
Okay. And we use what we've learned about significant figures to be sure that this value, the coefficient, contains the correct number of significant figures in it. So if we had maybe a 3 out here, we would have to include those zeros in that 3 in this answer. But since all of those zeros out here with no decimal first time, then 9.3 is it. But if we actually had a non-zero number in here, we would have to put the decimal there, but we would have to keep all of these in the coefficient. Okay. Let's see. When you're multiplying and dividing numbers with scientific notation, say we had 3.1 times 10 to the third and 6.0 times 10 squared. Right? You would multiply the exponent terms, whatever that would be. 0, 6, 18, like that. And that would be 18.6. Well, there are only 2 significant figures here, so we would have to round that to 19, wouldn't we? Okay, 19. And then when you multiply these 2 together, what do you do with exponents? Add them, right? So this would be 10 to the 5th. Yeah. So now you would have to, if you want to keep it in scientific notation, you've got to modify it again. 1.9 times 10 to the 6th. Okay. Starting to get bleary-eyed. Too much math for one day. No, we're going to use it. All right. The nice thing about calculators is you put the numbers in any way you want to, and it spits out. You can set your register up to give you the answer in scientific notation. Only you've got to judge how many significant figures you can keep. But the calculator will take in any numbers, do what you want to with them, spit it out an answer. So those rules that I just showed you, you don't always have to use them. It's kind of like Army training. They train you how to use GPS to find your way in a battlefield. But if you lose your GPS locator or something like that, you got to be able to read a map and move with it. So they teach you both ways. Let's see. I'm going to skip that one. Conversion factors. Okay. Suppose, let me think of an example. Let's keep it simple. Suppose I've measured something at 12 inches long. Okay. But I want to report it in feet. Now you know that 12 inches is a foot, right? But bear with me. I want to convert that length to this length units, but it's the same length. That doesn't matter. Why don't we make it a little more challenging? How about 36 inches? Okay, convert it to feet. All right, I need something that I can multiply that doesn't violate any of the math rules. That gives me this value. So I know that I can multiply that by 1. I mean, that's permitted, right? 36 inches times 1, but that doesn't give me feet. So what I need is an equivalence. What is inches and feet in equivalence? Well, 12 inches equals 1 foot. Okay, I know that. Whenever you've got an equivalence, you have the potential for a conversion factor. So suppose I divide this, both sides, by 12 inches. Right? I can do that, right? Anything you do to the left-hand side, you do the right-hand side, and you haven't changed the equivalence. So also, whatever you do to numbers, you have to do to the units too. So we divide 12 into 12 is equal to 1, correct? Divide inches into inches, they cancel. So that's 1. It's just a dimensionless number. But that 1 is equal to 1 foot divided by 12 inches. So I can substitute that for that 1, right? Because it's equal to 1. Right, so let me take it over here. 36 inches. Now I can put 1 foot divided by 12 inches in for that 1. Well, you know that if you write a number just on the line, it's understood to be in the numerator, right? It's always this divided by 1. That's the math rule. Well, if this is in the denominator and that's in the numerator, inches cancel, right? And you're left with feet. Now all you have to do is crunch numbers. 12 divided into 36 is 3. And you're left with these units of feet. So that's my conversion factor. And the lesson here is that conversion factors are always equal to 1. Every conversion factor is equal to 1 because of this equivalence. 12 inches equal to foot. 1 inch equals 2.54 centimeters. That's another possibility. 1 minute equals 60 seconds. 1 hour equals 3,600 seconds. So this is it in black and white and animation. I just put that there so we be sure and get it in there in case I forgot. Okay. All right. So you can convert within the metric system. You can convert between metric and English system. All you need is the right conversion factors and recognize that the quantity measured on this side is equal to the quantity measured on that side. It's just in different units. You haven't changed the physical reality by using a conversion factor. All right. I mentioned this one earlier. 1 milliliter equals 1 cubic centimeter. Exactly. They're equivalent. All right. What we've just done, this conversion factor thing, is the fancy name is dimensional analysis. And if you, there are many chemistry problems that can be solved by just following the train of conversion changes. Dimensional analysis can lead you to the right answer. If you have something over here and you have what you want, you know what we want to end up with over here, then the analysis is in between. Right? You just have to be consistent with math rules and consistent with physics. You can't defy the universe when you do things like that. Let's see. Right, I'm eating up time. I'm going to have to skip these. This is just a golf ball 6.8 feet across a green. How many inches is that? Right, to do that calculation. Converting mass, dimensional analysis concept check. Let's see. Right, I still got to talk about density and solutions. Oh, I will say this, so that I don't forget. When you're given a measurement, when you're making a calculation, measurements come in two flavors. They are either intrinsic measurements or extrinsic. The intrinsic measurement changes its value with the amount of substance. Example, if you have more gold in this hand than you do in that hand, then this one has a greater mass than that one. So kilograms of gold in this hand is more than kilograms of gold in that hand. That's an extrinsic value. Intrinsic values don't change with the amount of substance. So if I have that more gold here and less gold here, they both have the same density. Right? Grams per cubic centimeter is the same for both of them. That's an intrinsic value. Okay, so density is intrinsic, mass is extrinsic for that example. Okay. Conversion factors represent intrinsic. Density, as I mentioned, represents intrinsic. And very often ratios of things like concentrations are intrinsic because the concentration in a solution doesn't change if you have this much or if you have that much. Sometimes this one is called intensity factor. At least that's the way I learned it. It makes more practical sense to think of it that way. And this one is capacity factor. Or you could think of it in terms of, say, the Hoover Dam. Right? The capacity factor, or the extrinsic value there is how much water is being impounded behind the dam. Right? If there's heavy rains upstream, you have more water. But how much pressure is there at the bottom, that goes into the turbines? Well, if the water's at the same level, right, and you haven't moved very much, you could add more water to it and it won't move very much. But the pressure is essentially the same at the bottom. That was a bad example, wasn't it? Let's move. So think about solving this problem. Suppose you wanted to go from New York to Chicago. Now, I can't imagine anybody would want to do that. Right? Except that New York and Chicago are both hellholes right now. So you wouldn't be changing much by doing it. What I think of in terms is going from Beckley to Atlanta, where I have family. Right? So what would I need to know in order to calculate how much money I need to take with me just to drive the distance? Right? I have to know how far it is, right? Yeah. How much do I need to spend on gas? Right? Distance. I also need to know the price of gasoline. Yeah, you sort of have to take an average, don't you? Right. This is a big estimate. And one other factor. No, how efficient is my vehicle? Miles per gallon. If you know those three factors, you can calculate how much money you need to take with for one way. Then you double it, right? So you can sure get back. Atlanta's a big place, so I pad it with like 15 or 20% extra so I can drive around the city. You got to go 15 or 20 miles to get anywhere in Atlanta. It takes you an hour to do it, even with 8-lane expressway. So I only go back to visit family. I don't go, I'm not going to live there anymore. I've been weaned off big city. So there are the calculations. In this example, actually, that didn't make any sense. New York, Chicago, and then I do calculations for New York to Los Angeles. You know, I must have had a brain fart. But the calculation converts miles to dollars. That's the dimensional analysis we're doing. We got 3,200 miles to go. We have 25 miles to gallon. And notice that 3,200 miles, if we're going to convert that to gallons of gas, we know that our efficiency is 25 miles per gallon, but 25 miles per gallon, that's equal to 1, isn't it? So if we flip it and say 1 gallon per 25 miles, it's still 1. Right? So, but we need here to have miles on the bottom and gallons on the top. So I put 25 miles here and 1 gallon there. So conversion factors can be flipped if you need them. Okay, because they're equal to 1. Right? There's no harm done. So that's what we did with this calculation. And then once we have the number of gallons, we use an ancient example of cost of gasoline at $2.75. It's more like $3.75 now. Although I drove through Oceana on the way over here, and it was like $3.59. So I think I'll fill up on the way home. So I know it's more expensive in Beckley. But now we calculate in such a way that we cancel the gallons, and leaves us with dollars. And that tells us how much money we need to go one way. Which of the following is a feature of dimensional analysis? Well, units must be considered because they can be multiplied, divided, and canceled. Right? So anything you do to the magnitude of the number, you do to its units. Right? Multiply, divide, whatever. If you have to multiply two values together that have different units, what do you do then? Right? If you have something that's measured in meters, right, and you have something that's measured in seconds, what's your answer unit's going to be? Meters, seconds. Okay. If you can't cancel them, you have to keep them. All right. So I don't want to leave us hanging with our labs. Let me try to get through this thing. We'll talk about density now. I think that's the last concept, isn't it? Yeah, density. Okay, so I picked density as an example here because it's a formula, right? It's an equation. Density equals mass divided by volume. Okay. Anytime you have a formula like that with variables in it, you can rearrange that to solve for any one of them. Right? So we could solve for mass, and that would be density times volume. Right? And we could solve for volume, and that would be mass divided by density. Now, when would this be valid? Well, if you've got three variables there and you know two of them, you're given values for two of them, you can solve for the third. That's true for any algebraic expression. If you have an expression in one unknown that's left over, right, after you plug in numbers wherever they're supposed to go, one unknown, you can solve it. And that's the only type we're going to do. I mean, if you've had algebra, you know that you can solve two unknown equations as long as you have two simultaneous equations in two unknowns. Then you can solve that one. But we're not going to go there, right? You're going to have examples where you know all the values except one, you can solve for it. And so does anybody have any misgivings about solving algebraic expressions? Because we're going to do several of them. Okay. All right. So that's where we're going with density. Now, density, of course, is going to be an intensive property. Because if you know the mass of a substance and the volume of it, you do the ratio, that density value will not change. Right? You can have more mass, but you'll also have more volume as a consequence. So the density is constant for the substance, assuming all other things are equal. Like you don't change the air pressure, you don't change the temperature and things like that. Then the density is an intensive property. But this is an extrinsic and this is extrinsic. But when you ratio the two, you get an intensive property. All right. So if this mineral has a mass of 17.8 grams and a volume of 2.35 cubic centimeters, what's the density of the mineral? And that's typical. If you're talking about a solid and you're doing a density, it's usually grams per cubic centimeter. If you have a liquid, the expression is usually grams per milliliter. Now, the numerical value would be exactly the same, right? Because milliliters are equal to cubic centimeters. But by convention, solids are grams per cubic centimeter and liquids are grams per milliliter. All right, so there's our equation, and we know the mass and we know the volume. All we have to do is divide, and the unit of measure is grams per cubic centimeter. Right? We can't cancel them, so we have to keep them in the same mathematical position that they were before, right? Grams in the numerator, cubic centimeters in the denominator. That's our unit of measure. If we have 49.6 milliliters and its density is 0.85 grams per milliliter, we got this one, right? And we've got this one. So we would solve using this expression. So you can either solve for the unknown and plug in the numbers, or plug in the numbers and solve for the unknown. Doesn't matter. Works both ways. Right? So we can calculate the mass of that substance if we know the density and the volume. All right. Oh, I forgot temperature. All right. Hopefully we can get done with our labs without too much trouble. These are the systems of temperature that are used. Celsius, Kelvin, Fahrenheit. Fahrenheit and Celsius are radically different from one another. And I don't think I have time to go into the history of their development. I will say that Fahrenheit was invented first. The Fahrenheit thermometer was invented first, and it was primarily designed by Herr Fahrenheit to allow him to measure living systems. So his 0 point was the coldest he could get it, like ice and salt. Right? That's as cold as he could get it, that's 0 point. And the 100 point was what he considered to be typical body temperature. Right? We know it's 98.6 now, but he chose 100. I don't know how he calibrated 100, right? What he used to calibrate it, but he set it up. And then he subdivided 0 to 100 into 100 divisions. The next one to come along was Celsius. It was developed by a chemist / physicist. He was interested in physical phenomena. So what he wanted was an easy way to calibrate the system, his thermometers. So he chose 0 degrees as the freezing point of water and 100 degrees as the boiling point. And then he subdivided that into units. Kelvin came along a little bit later. And what Kelvin did was simply take the Celsius scale and shift the 0 point. So instead of 0 point being at freezing point of water, he made 0 absolute. That's as cold as you can get. Can't get any colder. Right? Now that's theoretical. It has to be. How do you get something to get colder? You shift the energy or the heat from that substance into something that's colder than it is. Right? That's the way we do it. So this can't go down to 0 degrees because there's nothing colder. Right? So 0 K, we don't say degrees, 0 K is a theoretical 0 point. The advantage is that in the Kelvin scale, all the values are positive. There are no negative numbers. And we need that for some calculations, because if you start introducing negatives in there, you get a mess. It just doesn't work. So I'll point that out. When we do calculations that need Kelvin, I'll tell you. Right, when we get to gas calculations. All right, so how are they related? Well, if you've got something at a given temperature, right, say body temperature, it's not going to change. The scale is changing. So 37 degrees Celsius is 98.6 degrees Fahrenheit and 310 degrees Kelvin. Excuse me, I misspoke. 300 K. Don't say degrees. All right. If we were go down to absolute K, 0 K, then on the Celsius scale, that'd be minus 273 degrees Celsius. So if you wanted to convert K and if you wanted to say K equals Celsius, whatever the temperature is, you would have to add 273 to it. Okay. If you were to convert Celsius into Fahrenheit, you need a more complicated formula. So the Fahrenheit degree would be 9/5 of the Celsius plus 32. That's the way I learned it. Your book may say 1.8 here instead. Same thing. So what we're doing here is we're adjusting for the size of the degree. Right? The Celsius degree is 1.8 times the size of the Fahrenheit degree. It's a different distance for each degree. But the 0 is shifted also. The 0 is shifted by 32 degrees. Right? 32 degrees Fahrenheit is freezing point. 0 degrees Celsius is freezing point. So that's what the 32 is for. And then the 9/5 is for adjusting the size of the degree. And if you know that formula, you can solve for either one of them. Right? Just say, if you know C, fine. If you know F, plug it in and solve for the other one. All right, there are the conversions. Right? And I put this link at the bottom. If you want a better explanation of how that's developed, that's a good place to go. It'll give you an explanation. All right. This is an interesting problem. Since their degrees are different sizes, their slopes are different, and they will intersect at some point to where the numerical value of C is equal to the numerical value of Fahrenheit. And this calculation, you just set each one equal to X in that formula and solve for X. And that turns out to be minus 40. So minus 40 degrees Celsius is minus 40 degrees Fahrenheit. It's environment. Once a month at this company I worked for, we had to do inventory. It was a hotel, restaurant, supply house. And I was the low man on the totem pole, so I had to suit up and go in the blast furnace, the blast cooler, the freezer, and inventory. So I go in there for maybe 10 minutes, 15 minutes, and inventory what I could before I started freezing. Then I come out into the cooler and warm up. So minus 40 degrees, it's very cold. All right. Significant figures. Let's see. It depends on your measuring device. as to which digit is the guess. Some thermometers are calibrated in tenths of degrees. Most are calibrated in just degrees. So you would have to estimate between the degrees. If it's tenths of degrees, you can estimate to hundreds of degrees. Electronic thermometers are very nice because they spit out the values and you don't have to squint to read them. Let's see. Okay, concept questions. I think these are the end. This concept question number 1, if an individual takes 300 milligrams of trazodone, anybody know what trazodone is? Huh? Yeah. It can serve, its side effect is nice because it's sort of like a tranquilizer, a calming agent. Yeah. They gave it to my son when he was going through puberty. He went berserk. We had to send him off to a residential treatment facility near Chicago until he got over it. And they used trazodone to calm him down. But trazodone of that amount each evening before bedtime for 1 year, how many pounds of trazodone would be consumed? And do the calculation, right? You figure out 0.241 pounds is it. If you want to see how that's done, I'm running out of time. Look at go into the archive videos and just fast forward till you get to that point and you can see how the calculation was done, because I've eaten up too much time and I can't finish the discussion there. Or this one. All right, so next thing we need to do is talk about the labs. All right. So let's see, do I have a... No, I don't have a lab there. All right, in the interest of time, what I'm going to do, pull out the one that's marked safety. This would be lab 1. Safety. I'm getting my copy. We'll go safety. So there's the only thing that's going to be here. I'm not sharing a screen, so if I don't write it up here, you have to reference this is my key, but this is what it looks like for the benefit of our viewing audience. Safety practices in the lab. If you have a limited storage capacity in your brain, remember this one rule. The best way to ensure safety in the lab is to prepare, to know what you're going to do before you come in. So it's not so important for this lab or introducing graphing techniques, but when we get to the third lab, where we're actually doing things in the lab, you need to study that thing ahead of time so you know what you're going to do before you walk in the lab. Preparation is rule number 1. In fact, in my general chemistry classes, we have a lab notebook that they have to prepare. They have to fill in whatever they can and make space for things in their lab notebook so that I know that they've reviewed the lab. And I grade them before they can even start the lab. So I'm depending on you guys to read the lab and be prepared to do it before you walk in. Then there are other things that are some more essential than others, depending on the lab, is to know what you're going to do ahead of time in an emergency. Prepare. Right? Think like an EMT. Right? What do I do in this situation? I don't have time to think. I just have to know what to do. So if a fire alarm goes off, we've got two exits, right? One at that end, one at this end. Know where they are. If you catch fire or you get splashed by some corrosive chemical, know where the wash and the shower are back there in that let's see, northwest corner. I've got north marked on this table. As long as it doesn't move the table, it's accurate. Right, so that's north. So it's essentially northwest corner. So know where those things are, and be sure that if you're gonna do the shower thing, be sure you need it, right? Because it's going to dump gallons of water in seconds on you. Okay. Eye wash is a little more conservative. Fire, catch fire, you need a fire blanket, know where it is, right there on the wall. Know how to use a fire blanket, grab that handle and start turning. And it'll feed out of the thing and wrap you in it. And then you can stop, drop, and roll. What else? Know where the telephone is, right here, if you need to call for help. So know in advance what you're going to do. Be able to recognize hazards. That's another key factor. When you're reading through the lab, and you're going to go into the lab, many of these labs have a blurb on safety in them, built in. Right, so that'll help you. Never work alone in the lab. Always have a partner. Don't get creative. Unless you talk to me first, and then we may find that it's okay. We'll make adjustments in the method. Clothing, right? You need closed-toed shoes, no sandals. You need your legs to be covered, right? So I know shorts are comfortable this time of year, but you need long pants or a lab coat that covers your legs. I've got a lab coat that goes down to my knees, and then beyond that is my pant legs. So you've got a barrier between you and any spills. When we're actually doing lab exercises, all food and drinks, bring them up here if you need. Right? Just set them up here, then you have access to them, and they're away from the experimental area. We'll have places to dispose of waste materials. Usually I'll have a beaker marked waste. That's where you put your waste. Unless I tell you it's okay to go down the drain. Right? If it's non-corrosive, it's non-toxic, if lots of water will neutralize it, then sometimes we can just, solution to pollution is dilution. Keep a clean work area, right? If you're going to use a Bunsen burner, where do your papers need to be? Over here. Yeah, right on top of the burner. Yeah, that's funny. Fume hood, we probably won't have to use the fume hood, but maybe once or twice. Just if we have some fuming chemicals like concentrated hydrochloric acid or ammonia, something like that. Otherwise, everything you can do on the bench. Watch out for heat sources too. Right? We use Bunsen burner sometimes. We use hot plates other times in boil water. We may need a boiling water bath to conduct an experiment. I kind of hate this expression, use common sense. Right? Common sense to one person is not common to another. So you have to start thinking like a chemist. Right? Develop an intuition for what constitutes a hazard and what is essential to accomplishing the goals of the experiment. And your experiment needs to be as simple as possible. Right? In sciences, we call that elegant research. Right? If it's elegant, it's very simple. And it gives you a lot of information with a little effort. So the experiments that we perform, the procedures, are not going to be that complicated. It's what comes after that may seem complicated. What do you do with what you got? you're looking for an answer, and you've got all this data and observations. How does that lead to the answer? Right? That's where the real science occurs. Let's see. We're not going to be working with any glass tubing or trying to fit them through holes and stoppers, so you don't have to worry about that. But if you ever have to do that, lubricate the glass with a little water, go through a rubber stopper once the hole is plugged, and usually hold it with a paper towel, something, a barrier between you and the glass in case it breaks, and hold it close to the stopper. Right? The farther away, the more torque you put on it. And high torque means broken glass. So hold it close to the stopper and push a little at a time, if you ever have to do that. If you're going to smell something, right? Yeah, waft it. Don't stick your nose down in the tube. Material safety data sheets. I think they call them material safety data sheets now, just SDSs. They're in those black binders over by the barometer, that wooden box that doesn't work anymore. If you want to know details about any of the chemicals we're using, those safety data sheets are there. Chemical spills, right? If you get something in your eyes, you want to get it, you want to flush it as quickly as possible. Lots of water for 20 minutes. Okay. Yeah. Hopefully your eye protection will alleviate some of that. Maybe you only get some splash on your skin somewhere. And we won't always have to wear gloves, but if we're dealing with hazardous materials or hot objects, sometimes those nitrile gloves are all the barrier you need to hold a hot object for just a second or two, right? Rather than the big bulky gloves, because the bulkier the gloves, the more likely you are to spill, right? So there's a trade-off there. You want to watch out for electric shocks. Right? Just plugging stuff in and pulling it out is basically when it happens. Cuts and wounds. Has anybody had first aid in here? Okay, so we got a couple. Okay, good. So you know how to deal with injuries. So yeah, it's kind of dim in my memory too, but we used to have to do first aid training every year for the U.S. Department of Agriculture, where I was a researcher for 22 years. And they'd give us a day off, and we do our first aid training. We do CPR at the same time. And CPR changed over the years. I can remember how it was in the beginning, and now you don't even do breaths. Right? You just staying alive. Supposedly, as long as you keep the blood flowing, there's enough oxygen reserve in your other tissues to keep your heart and your brain from going anoxic. So you don't have to breathe. And that's good, because a person that's had a heart attack, most likely when you start pressing on their chest, they're going to vomit. Right? So the first solution to that was these little devices that have one-way valves in them. Right? But then they decided that wasn't even necessary. And then, of course, when the EMTs arrive and they relieve you, they don't do mouth-to-mouth either, right? They have oxygen, and they have a mask and a bag, right? And they're better equipped. Okay, so safety information on page, it looks like page 8 here. The shower's I said it's in the northwest corner. Fire exits are in the northwest and southwest corner. Eye wash is in the northwest corner. Fire extinguishers, where's that? West wall, right by the fire blanket. Okay, those are ABC. That's an ABC extinguisher, which means what? You can use it on anything, right? I forget what the A's and the B's and the C's stand for, but it's safe to use here. It's basically ammonium phosphate. Right. So what you need to do is, if it's been sitting there for a while, before you use it, tip it up a couple of times. I mean, it may take it. You may lose a little time with the fire, but it's better than pulling the handle and nothing comes out. So mix it a couple of times and then go. First aid station is on the west wall. It's over there by that big gray pillar. Actually, there are two of them. Fire blanket is on the west wall. Material safety data sheets, they're on the northeast corner on the bench. The nearest phone is on the instructor's desk. And I've got some telephone numbers here, but I'm not sure if they're valid anymore, right? For fire, these are all 304 area codes. Fire is 752-3601. It's local fire department, I guess. Poison center is probably located at the hospital. 831-1101. And police, unless they've changed, is 792-8590. I don't have any additional instructions there. The last thing I need from you, and you can give me this next week, is this safety agreement. So read through those points, those 15 points on page 9, and then put your signature, the date, the course that you're in, the lab section. Don't worry about that one because we haven't divvied up into labs yet, into partners. Locker number, we don't have a locker number yet either. In fact, somebody emptied all my locker buckets. You pull the buckets out, right, and take them to your desk with stuff that you need. They're empty. I'm gonna have a talk with somebody. So leave that one blank. Room number, right? What room number is this? It's building A, 234. Then I'll sign it and date it and keep that in my records as our safety agreement. Then the other thing that you need to do to finish it off is answer these questions. This quiz at the back. Most people get pretty high scores anyway. So if you were paying attention, right, you'll get most of them right. And the last one is a scenario. Number 7, it describes a laboratory scenario, and you're supposed to pick out what was done wrong. And there are 9 points, so you're looking for 9 things that were done wrong. Okay? All right. So that one is due next week, and the next week for lab, we're going to do this one, introducing graphing technique. Once you get finished with that one, you can dig into this one and look at it, read it. I'll do a discussion on this one in lab next week, and then you'll have the following week to work on it. This one has bonus points in it. It's got a required section and a bonus section, so you can rack up the points with this one.
Yeah.
Question? We're ahead of time, right? We could go to 55, 12:55. But if there are no questions, I'm okay if you want to go. Time flies.
That's fine. So this here, do we just work on it at home?
Yes.
All right.
Bring it to class next week and turn it in.
So how often do we use our buttons?
Follow the schedule, and if we're going to have an introduction of chapter 1, chapter 2, read those ahead of time, like we did today. Chapter 3 is next week, so read chapter 3.
Okay.
Yep.
Do we need to bring the book to class?
You don't have to. Now, all of those, the review document has questions on all 3 chapters.
Okay.
So until you get introduction to chapter 3, the review document for those questions probably isn't going to make a lot of sense, right? So if you don't understand a question in the review document, just skip it. Go back to it later.